So now we are live on YouTube.
The following message is best viewed on an oscilloscope.
So, greetings from the Czech Republic. I want to welcome you at the conference ICHEP 2020. It is a big pleasure for me to be chairman of this session. My name is Miroslav Schulz, and we spent one afternoon in Central Europe, 5 hours together at our session, which is concerning about technology application and another opportunities for industry, which can be used at different possibilities. And now we have our session divided to 2 blocks. The first one is concerning mostly about the detectors, mostly about the gaseous detectors and software, which is used at first for high energy physics community, but also for another possible communities. It's very, very important. And after a coffee break, we will continue with 4 talks concerning about the application of some methods and detectors used standardly at high energy physics. We will see how to use it at the monitoring of some particles around the Earth, at the volcanoes, and something which is concerning about the medical application and laser acceleration. So we can discuss about our problems and topics immediately after end of the talk. You can use standard Zoom and or Zoom chat, and you can pick up a hand if you want to give some questions. But the time for this type of discussion is limited, approximately for 3 minutes. And of course, we can discuss at this Zoom during the coffee break and after end of the session for people which are not able to use this Zoom chat. We can use also the chat of Mattermost, and it is possible to use this Mattermost chat channel for the discussion during the next presentation on after all talks. We can use it almost at all time of our session. So it is fine that the first speaker is Dr. Katsioulas, And the first presentation is the presentation about fast neutron spectroscopy with a nitrogen-based gaseous detector. Please, you have the stage.
Okay, thank you very much. Very happy to be here. So, as you said, my name is Ioannis Katsioulas. I come from the University of Birmingham to talk about one of our recent efforts, the development of a fast neutron spectroscopy system using nitrogen gas and a spherical gaseous detector. So, the neutron detectors, there are many types of neutron detectors. Neutron detection dates back to the discovery of neutron itself, but I will only talk my introduction about a few of them that are very popular and relevant to what we are doing. So the most popular neutron detector technology is based on helium-3, which is the reaction type detectors. This means that the neutron will enter a detector, it will be absorbed by the target, and then the target will spallate, producing a few charged products that will induce ionization in the detector, and this way we can measure a neutron. Also, same type are BF3 Boston counters. Also, we have the recoil type detectors, which usually filled with methane and helium. Here we have the neutron being scattered on a target nucleus. Then the nucleus recoils and ionizes the gas, and this way we measure again the presence of nucleus. The gas detectors are very popular neutron detectors because they have many advantages, good efficiency, but also can offer good neutron gamma discrimination. So one would ask, why do we want another neutron detector? I will explain this briefly. So neutron detectors are lately very popular, especially for national security reasons, and especially helium-3 ones, which created a huge shortage of this material, and now it has become extremely expensive. Governments and industry are searching for an alternative, which is sometimes is BF3, but a big advantage of BF3 is that it's highly toxic and is not usually allowed in sensitive environments. Also, these kind of detectors have low target mass and cannot completely stop reaction products inside the volume of the detector. So the most popular method is to moderate this, to use moderators of neutrons around these detectors and measure the thermal neutrons, which these detectors are very sensitive to. So what we want to do is to propose another detector, another method to measure fast neutrons, which will be simple. When I say simple, I mean with few components and easy to construct, and we have a very robust construction, so it can be used in different kind of environments. A detector that will be easily operated by few people that don't have to be experts and that are very easy to deploy and don't have to have complicated shieldings, and also safe, which means that we don't want to risk the health of working around the detector with toxic materials, and also with detectors that contain gases in very high pressure. So for this reason, we have an idea to use a large volume spherical detector filled with nitrogen. So a detector like that can be operated in pressures over even 3 bar, has quite large volume, depending on the size, can reach even 1 cubic meter, possesses the same attributes like helium-3 detectors, as for example, good neutron gamma discrimination, and has even higher stopping power than helium. Also, nitrogen is a cheap, non-safe, non-toxic gas and can be used everywhere. And we intend to operate this detector without any moderation, so we can measure neutron energies. So let's look at the cross sections of this for these reactions. Here you see the 4 cross sections we are talking about. The workhorse for our detector is this N-alpha reaction of nitrogen. I don't know if you can see my cursor. Can you see my cursor?
Yes.
Yes, we can.
Okay, thank you. So this is a workhorse which combines the two advantages of the above reactions: the low Q value of the helium-3 reaction and the alpha product that has very short range of the boron reaction without the disadvantage of the high Q value, which spoils the resolution. And as you can see, nitrogen cross-sections may be a little bit lower than helium-3 and boron in some places, but they are quite comparable. And while nitrogen doesn't have the high cross-section of helium-3, it still has a good cross-section for thermal neutrons, so it can be used as a thermal neutron counter. So let's talk about the detector. It's called the spherical proportional counter. It's a particular detector that was recently developed. The spherical cell is grounded, and in the middle of the detector we have a small anode supported by grounded rod through which we pass a wire to apply the high voltage and read out the signal. Due to the configuration of the electric field, we have a relatively low electric field in the volume of the detector where the primary ionizations are created. Then electrons will drift towards the small anode in the middle, and due to the reverse of the radius square dependence, we have very strong fields close to the anode where we have very strong multiplication. Another feature of this detector is that it has, even for very large detectors, we have very low capacitance due to the dependence only from the radius of the small ball in the middle and not on the whole volume. This is the type of sensors we use in the simplest case. As you can see, is the anode, a correction electric rod, in this case made of resistive glass, and the metallic rod. Here you see it in the implementation in real life. More information can be found in these two publications. So one big advantage of this detector is also in that in the pulses, in a few pulse shape discrimination parameters, we can have a lot of information, such as amplitude, the rise time, and the width. When I'm talking about rise time, I mean the time it takes to collect all the electrons of an event. And I want to show you an example of this. So you see, using this information, we can have event discrimination, especially when it has to do with extended and point-like tracks. And also we have visualization, meaning that we can get information where the interaction took place inside the detector. Here you see the example of long track events, in this case cosmic muons, and point-like events, in this case argon recoils. Both have the same amplitudes, but as you can see, if we take into account the width, we can clearly discriminate events of the same energy position. So we intend to use these features for this Newton detector. So the detector is very flexible. It comes in sizes. It can range from a few centimeters to 200 centimeters, as you can see here. It can be made with a number of materials: steel, copper, aluminum, glass, and vary the sensor size depending on the application. It can be filled with many gases, more than I have included here, and can work in low and high gain to detect alphas or X-rays. The applications that this detector is used various and ranges to gamma ray spectroscopy to dark matter detection, which is I'll talk about later. You can see here different detectors in different parts of the world. The first prototype ever made in ICHEP. You see here the inventor of this detector, Ioannis Giomataris, testing it with George Sarpak. A detector in Saragossa, Arthur MacDonald with their detector in Queens, the News G detector at LSM France, and the one we tested in ICHEP. The most notable application of this detector is the snow globe, the News G detector that is used to perform light dark matter searches with very high sensitivity. Here is the collaboration, which I'm a member of. If you are more interested about this, you can follow the presentation of Patrick Knights later today. So, Newton detection. So, one of the first application of this detector back in 2015 was the neutron detection with this spherical counter. This is the first prototype used. This detector was filled up with a few hundred millibar of nitrogen gas. And then we used fast neutron sources such as californium and American beryllium to try to measure the spectra. And also did thermal neutron measurements and pressures. But the pressure was not high enough to contain all the parameters. This was the main drawback then, the wall effect. Of course, we try to increase the pressure so that we reduce the wall effect. When I say wall effect, it means that our reaction products touch the wall, so we lose a part of their energy. As you see here, we have the example, the American beryllium spectrum, the theoretical one, and the one we measured. You can see that for higher neutron energies, we kind of lost the information of energy due to this wall effect. Increasing the pressure had induced instabilities in the detector, and also the impurities then in the gas had the effect of low charge collection. This was a stage that the technology again then was quite immature for this kind of works, but we're trying to improve that. So this is what I was thinking about the wall effect. You see the protons especially have high ranges and touch the wall. And so it's critical for us to contain as much as we can to reduce the range of the particles, so we reduce the percentage of the wall effect. So to do that, we exploit now recent developments of the spherical proportional counter, as it is the resistive sensors that can reach very high voltage of operation without instabilities. The multi-anode sensors that have also stable operation in high gains, but can also increase the volume electric field. And we include gas purification to reduce impurities to minimum. So the electric field strength is key to this application because nitrogen gas is notorious for the difficulty of the detectors to reach appropriate gains in it without having the very high voltages. So the thing is that if we try to increase the pressure, we have to increase also the electric field. And this also has to do with the collection of electrons. As you see, the drift of electrons needs also increase the electric field for higher pressure. But to do that, we have a few options. One is to play with the radius of the anode. But if we do that, we may increase a little bit the electric field, but quickly we will lose the gain capabilities that we need and are achieved with smaller diameter anodes. So this was a conundrum that we solved using this module, the multi-anode ICHEP sensor. So this is the design. There are few balls placed in the same radius around a central electrode. The central electrode is also putting high voltage, and the balls are in equal distance between them. And now the electrons liberating the volume of the detector see the collective field from all these anodes. But when they are reaching closer to the sensor, they will see only one ball, and the gain will come from this separate anode. This way, we manage to decouple the need for high field and high gain that was given by the size of the ball. You can see here the effect of the achinos. I forgot to say that the name is a Greek, comes from this the sea urchin, the animal that inspired the design. So the name of the achinos sensor, you see, we can tune the electric field in the volume by including more anodes or increasing the distance from the sensor sender, and we can tune the gain by playing with the anode size and putting smaller anodes. And if you can read out the balls individually, you can even give TPC-like capabilities to the detector. So this is the achinos features. You see, you have a quite nice resolution for the 5.9 keV of iron being measured with the achinos. in 1 bar of argon. So we constructed by designing it by using FEM simulation software like ANSYS, and then passing this design to a 3D printer to construct an accurate module. As you can see here, you see the implementation, and the plastic is covered with a DLC layer to apply high voltage on. You can find information in these two publications. And with this module, we achieve very nice resolution. We can operate in high pressure with high gain if required, with stability. For the gas purification, we have used commercial and custom-made filters to remove electronegative gases that cause attachment and loss of slowing down of the electrons. You can see an example here of the use with helium gas. This is the line of iron source measured with a detector without any filtering, and you see the line blurred. But when you include a filter, the detector has a much better resolution and a much higher gain, as you can see if you compare between the two conditions. So we managed to solve the impurity problem also by minimizing them to parts per trillion. And now we also developed a very advanced simulation package that combines all state-of-the-art toolkits into one, like FEM simulation software, Jan4 and Garfield, to to simulate every procedure that takes place in our experiments. So we have Jan4 to transport particles through shieldings and until it enters the detector and measure and then interact with the gas and deposit energy. Then Garfield takes place to simulate the operation of the detector, like the electron drift, the multiplication, and then we have the FEM software to model a very accurate electric field, realistic, and to simulate the avalanches. A lot of information can follow. For more information, you can follow the talk of Tom Nip on Friday. You can find it here. So this simulation will give us the detector response. You can see here pulses the induced current created by interaction in a simulated interaction in the detector. Then we can include the transfer function of electronics, and then we have realistic pulses that are similar to the real measured pulses, and we can treat them with the same exactly software in the same way that we treat measured pulses to study the detector operation. As you can see, we can correlate variables like rise time, as I explained before, in the pulse integral, with variables that we cannot measure in the experiment, like the radius of interaction, giving us a lot of information about what takes place in our detector. So we use this software package to simulate our neutron interactions. You can see here a thermal neutron entering the detector and then producing our protons and produce pulses. In this case, we have a 30 centimeter detector in diameter filled with 300 millibar of nitrogen. And then in the same conditions, the interaction of a 4 MeV neutron and the production of alphas and protons inside the detector and the pulses. Here you see the same thing, but the histogram of all the amplitudes of these interactions, of the pulses, and the rise time versus amplitude. And you can see by using the simulation, you can understand the response of the detector and which pulses are induced due to Wall effect and other processes that take place inside our detector. Same for sorry about that, with the 4 MeV neutrons. So you have here the alphas coming from the N-alpha reaction, the protons coming from the N-proton reaction, which are much lower amplitude due to the Wall effect, due to the high range. And you can see this information here, where you see that how we correlate the rise time and amplitude with with the radius. Let's say the color is the last electron created in the detector, and you can see that protons reach the wall of the detector, while alphas are much more contained inside the volume. And this is very good for us because this is our goal, to detect the alphas and to reduce events coming from wall effect from alphas. So using this simulation, we plan to do two things. One is to actually study which conditions are optimal for sensitivity versus wall effect, and to unfold eventually the spectrum of our detector. So in Birmingham, we have a whole system for spherical protospheric counters. We construct our sensors and we characterize them and test them there. Here are a few examples of calibration that is done using triple alpha sources. And we plan to operate soon to 1-2 bar to minimize wall effect and to increase target mass, and to take our detector to a neutron generator that can produce monoenergetic neutrons that will be used to study the response and validate the simulations. Here is instrumentation done in Birmingham. We can do everything for spherical proportional counter, from the sensor that here he knows that's going to be installed in the detector, this detector that we produced, and the filters that we make using molecular sieves, this time in collaboration with the University of Liverpool. So the first application for our neutron background spectroscopy system is neutron background measurements in Bulby. Bulby is the National Underground Laboratory of the United Kingdom. You can find it here in the northeast of England. It's 1,000 meters. It's a working mine, 1,000 meters below the Earth. There is the lab, and there we installed this aluminium sphere that I showed you before, along with a full gas system and the electronics that are used. That are the same electronics that we use for the NEWS-G experiment that we perform dark matter searches. So because, and also it's a direct transfer of technology from high energy physics to technology for society. So you see here the process of the installation and our team here, which were from UK and France. We plan to do rate effect studies and space charge effect studies there, measure the neutron fluxes in the environment with both thermal and neutron components, and include also energy formation for the first time. And we hope that this method will be very valuable for other laboratories that can be used and measure this very dangerous background for rare event searches. The problem was that the installation procedure and the characterization of the detector finished like mid-February. Then we had, of course, the stop of operations due to the COVID pandemic, and we expect to start soon the operations in Bulby. Things, I think, start up now. I hope everything goes well and we have results by the end of the year. So, to summarize, our goal is to produce a detector that can be considered as a very good alternative for fast neutron spectroscopy instead of using helium-3 and BF3 counters. We had very promising results with the first measure of the detector. The limiting factor was the wall effect, that we think that we are going to fight it with all the recent advancements we made for the spherical proportional counters for our high energy physics applications, and that this will allow us to go to even higher pressure and increase the efficiency of the detector, and also to use this detailed simulation toolkit that we produced to accompany this detector with a software that will produce the neutron spectra that you detect. Okay, I think that was it for me. Thank you for your attention, and I'm glad to answer to any questions now or later in the Zoom room. I have the link for here in the end of the day.
Mm-hmm. Okay, thank you for your presentation. So now we are open for discussion at our Zoom room or at private Zoom room, which is proposed by presenter. I have no message at the chat, and
I have one question actually.
okay, thanks.
If I may.
Yes, sure.
Okay, hello, this is Massimo Cazza from Università dell'Insubria and INFM Milano. I actually have one question. Usually, one of the potential applications for fast neutron detectors is actually homeland security. In such a case, it is absolutely essential to have a significant neutron gamma discrimination. Did you ever perform any measurement? Do you have any indication about this figure?
So yes, so let's see if I have everything in my backup slides for that. So I will use this as an example, but okay. So you see here cosmic tracks. You can say that these are electrons produced by Compton interactions by gamma, and these are the signal. So in our detector, when you used, for example, cesium source to produce gamma ray events in the detector, we have a very high efficiency to reduce this gamma background from pulse shape using pulse shape analysis. So it is possible to remove gamma events.
But I'm a bit confused because for standard scintillators or devices where you perform gamma neutron discrimination, you know that actually the two kind of particles are producing shapes that are different because of the different scintillation taus. And here, actually, how do you exactly imagine to do it? Which is the relevant figure that you use? Is the balance between fast and slow scintillation or anything else?
So we don't use scintillation yet, first of all. Just to explain, we use the
Yes, since you're not exactly the question, since you're not using scintillation, how do you discriminate between a gamma?
With pulse shape parameters that I mentioned, like rise time of the pulses and the width of the pulses, and more complicated parameters that have to do with the extent of the interaction. So because electrons would have longer tracks compared to the alphas of the same energy, or, you know, as I show here, you see. So we are going to, what we do usually is try to, to find the optimal parameter to remove tracks that are longer, more extended, and in different parts of the volume of the detector.
Yeah, the previous graph that you have been showing where you have the electron and then the alphas is very clear. Okay, thank you. No, but no quantitative estimate yet to the rejection.
Unfortunately, for the current detector, we didn't do this test yet. We did it in the past with the large detector, and it was, I think, quite efficient. I can point you to the first publication that we had. Sorry, where do I have it? Here, for more information.
Okay, thank you very much.
Mm-hmm. Okay, so thanks for question and for the answer. Still some questions?
I have a question.
Okay.
My name is Walter Snoeys, from Walter Snoeys from CERN. So you mentioned the wall effect, and I guess this was related to the charging up of the wall. Now, I thought that the wall was more a conductor. I'm not a specialist of gas detectors. Is this because it gets to be an isolator after some time? Or otherwise, I would expect it not to be charged as much. So what is the mechanism exactly for this charging? Is this because there are some residues deposited on the wall?
So when I'm talking about wall effect, it's if you have a track, you know, that starts from some point, like a proton, for example, it will eventually reach the wall, which is grounded and not read out, so we cannot know what happened to the wall. And this information is lost to us because we can measure only ionizations that happens in the gas volume. So when we say wall effect, it means the energy lost due to the energy deposited on the wall by the charged particle.
Ah, okay.
Yes, yes, yes.
Okay, thanks. Still some questions? Okay, we can end this talk, and thanks to speaker again. And we can go to the second presentation given by Roberto Guida from the CERN. This presentation is concerning about the strategies for reducing the use of greenhouse gas from particle detectors operation at CERN LHC experiments. Please, Roberto.
Okay, yes. Start sharing, share. Tak. Okay. So can you see in full screen mode now?
Okay.
Okay, very good. So I'm going to talk about our research for reducing the use of greenhouse gases in the LHC particle detection system at CERN. So I will, of course, introduce what are the greenhouse gases, how they are used at CERN, the gas system for the LHC experiment and the detector at CERN, the strategy for optimizing the usage of these greenhouse gases. Then I will discuss results, new project, and plans. So first of all, greenhouse gas is any gaseous component that is capable of absorbing infrared radiation and therefore trapping the heat and holding the heat into the atmosphere. Greenhouse gases are characterized by their global warming potential, which is a measure of how much heat a greenhouse gas traps in the atmosphere with respect to the CO2. Greenhouse gases like 134A, CF4, SF6, and C4F10, and others in smaller quantity, are used by several particle detector systems at the LHC experiments. Here you can see the global warming potential of these gases, and they are very high with respect to the CO2, of course, which is the reference at 1. So due to the environmental risk, fluorinated gas regulation started to appear in many countries. And for example, in Europe, there is this regulation 517 of 2014, which is trying to limit the total amount of this fluorinated gas used. Is trying to ban the use of fluorinated gases if other alternative or green alternative are available, and is trying to prevent their emission into the atmosphere from existing equipment by requiring check and proper service and recuperation of these gases. So the fluorinated gas regulation already started to have an effect on the price of the gases, and they may have an effect on the availability. So this is the few plots concerning the European regulation for fluorinated gases. You see here the effect of the reduction in availability over the LHC operation time, so up to 2030, when the availability or in quantity of these gases is going to be 1/5 to what it was in 2015. This is by the imposed by the regulation in Europe. Other effects are, this is more illustrating the availability of the gas as well, where you see that here the production together with the recuperation are decreasing because the industry is moving to green alternatives. On the other hand, there is also an import from outside, so mainly from China and from USA, which is still going down, which is again going down. So, industry is moving to other alternatives. And here you see fluctuation in price. In 2017, we had an increase because this regulation started to have an effect where from 17 to 18, there was the biggest step from 93% to 73% of the quota available. And now, I mean, the price is decreasing a little bit, probably because the industry, as I said, is moving to the new alternatives. Moving to the gaseous detector system at LHC. So the detector system are open in a wide range of volumes from a few liters, few hundred liters, up to several hundred cubic meters. So it's quite big range. As I said, that they are using greenhouse gases, but also there are other gases, neutral gases, but expensive are used. For example, xenon. So if you combine the high mixture flow that we have in the detector because of the large detector volume and the operational cost of these gases, I mean, optimizing the usage of the gas was mandatory since the design phase. And in fact, it was done at the beginning. Otherwise, without any optimization, the cost would have been simply impossible, as we see also in the next slides. So relative contribution of greenhouse gases used at the LHC experiment is illustrated in this picture. So the large part is the R134A. Then we have contribution from CF4 and SF6. Concerning detector, I mean, main contributor are the resistive plate chambers because of the very large volume and also the presence of leaks, then the cathode strip chamber, then GEM, and so on. I mean, of course, you have to say that the greenhouse contribution usage in particle research is negligible. It's basically zero with respect to other activity. Nevertheless, it's important to optimize the consumption because, I mean, it's the gas that we need. So it's basically, the objective is also to secure the operation for the years to come and also to have operational costs which are acceptable. So a few words about the gas system. The gas system are very large apparatus at CERN. They are mixing different gas components as required by the detector, and this mixture is distributed to the individual chambers. The gas system are made of configurable functional modules, so these building blocks that you see in the picture. And the goal is to simplify the maintenance, the operation, the training of the personnel. So I would like to stress three keywords about this infrastructure: reliability, because it has to be always available for the data taking, like many others, of course. The automation, because such a big infrastructure cannot be sustainable if it's not fully automated. And the stability, because I mean, reliability of detector and data taking relies also on this infrastructure. The system extends from the surface over several hundred meters up to the experimental cover, where we have the final distribution modules, which are serving the individual chambers. One system is about 10 functional modules. In total, we have 300 modules for the LHC. So if we put one on the top of the other, it's basically twice the height of the Eiffel Tower, just to give a size of the infrastructure. Now, back to the greenhouse gas and the optimization of their usage, we identified 4 strategies. The first one is optimizing the current technology. The second one is developing recuperation system. Third is looking for alternatives, so green alternatives. The fourth one is disposal. Disposal is, of course, is not optimization of the use, but at least is reducing the emission into the atmosphere. So first step, optimization of the current technology. So as I said, the first step was already done at the design phase, where most of the systems were designed to recirculate the mixture. So the mixture was passing through the detector, and after the detector was recollected, filtered, and reused. So the advantage of this strategy is a reduction of the consumption, a reduction which is in the order of 90%, because this is the average recirculation fraction. The disadvantage is the complexity of the system, because we have to deal with the pressure regulation into the detector. We have to filter the gas which is coming back. We have to be sure that the gas is not polluted at any level. So we need a constant monitoring hardware and also mixture composition, meaning analysis, also chemical analysis of the gas. And also sophisticated gas purification techniques, because they have to deal with a cubic meter of gas per hour, 24 hours per day, 7 days per week. So the remaining 10% is what we started to address from LS1, so the long shutdown one of LHC. And it is needed to compensate for leaks because we have leaks at the detector level in few systems like the Atlas and CMS RPC, and also to compensate for the nitrogen intake that we have in other detectors. Two remaining systems were in open mode, so the gas after the detector was exhausted, and have been upgraded to gas recirculation from run 1 to run 2, so during the long shutdown 1. The first one of this system is the Alice resistive plate chamber trigger, muon trigger. The mixture used here is mainly composed by the 134A and the SF6, a little bit of SF6. It was started in open mode because the detector volume is quite small, 300 liters. And this is, but it was upgraded to gas recirculation in 2015. So if we do a little calculation, we see that the original investment for the upgrade of the system is largely paid back by the gas cost saving during these 5 years of operation. So it was the right decision to go for everything. So I mean, in fact, from run 1 to run 2, we had a reduction of the greenhouse gas emission from this system of 75%. Nevertheless, the RPC in Alice are operated in a slightly different condition, which brings to higher pulse charge. And the higher pulse charge is bringing to impurities, to the fragmentation of the main gas components, so the formation of impurities that we have to monitor because they may affect the detector performance. This was not the case. The impurity was monitored. And if you want more details, you can go to this presentation. So it's just to say that recirculation also requires close monitoring of the mixture. The next one was the LACB system, the LACB GEM system. Here the mixture is mainly, the greenhouse gas component is the CF4, is present in 40% of the mixture. The GEM detector is very small, I mean, less than 100 liters, 50 liters. But GEM requires a very high flow. And so this is why the contribution of GEM was very important, was comparable to other detectors that have 100 cubic meters of volume. The GEM detector were never operated before in gas recirculation. And this is why in 2013, we started to develop a small gas recirculation system to start an R&D about operation of GEM detector in gas recirculation. Here you can see some details about this development, this system that we developed. In 2016, we continued the validation of GEM prototype at the gamma radiation facility, where the background of the LHC experiment is simulated using an intense gamma source. And also we set up the purifiers for the GEM in particular. And in 2016, we moved and we did the real upgrade of the GEM system at LHCb. So these two steps, they went in parallel, basically. So again, also here, the decision was the best one to take. And in fact, the original investment already largely paid back by the gas cost during operation. And this is only in less than 4 years. In addition, the GEM detector operation became more stable because in open mode, there were frequent change of bottles, of CF4 bottles that were inducing for some reason that we never discovered the impurity because probably it was very small. They were inducing a change in the gain of the detector. With the new system, it was not visible anymore. So here with a 90% reduction. So now we come to the large Atlas and CMS RPC system. Here we are talking about 15 cubic meters, 15, 16 cubic meters. So they are much bigger than the previous. The gas use is the 134A, 95% plus the SF6. These systems are already operated in gas recirculation, fraction between 85 to 90%, depending also on the leaks, on the leaks at the detector. Okay. But here a further optimization requires, first of all, fixing the leak at the detector level. And this is not something easy. There is a huge effort ongoing from the RPC detector community. But you have to imagine that these leaks they develop at the level of connectors or pipe that are well inside the detector and very, very difficult to access without going to touch other part of other detectors. So it's very critical. There are good technical progress ongoing, but still the challenge is very high. Then, of course, we have to work on the gas system upgrade to minimize any pressure or flow fluctuations beyond original requirements. Work on the impact of the current ventilation. Any fluctuation can be dangerous for the detector. And also look for other external causes. We cannot exclude vibration because the structure is vibrating, and this might cause failure in the connectors. We have to study validation of operation at higher circulation fraction in case we will manage to reduce the leak. And we have to develop recuperation plans, because if we reduce the leak, we will have the possibility to either increase the recirculation or filter the gas, removing the impurities and the nitrogen, and reuse it. So all this work is ongoing, or is started, or something already done. We had an improvement of the pressure regulation by 70% reduction in the fluctuation. Unfortunately, we didn't see any improvement in the reduction of the development of leaks. Example here of the work on the distribution modules. So here is a typical distribution module. I will focus on the input of the gas mixture. Here are the detectors, and here is the output. So at the input, we modified the opening of the input valves to have it as low as possible, as gradual as possible. In new modules, we introduced the regulation valves to have the possibility to tune at our desire. At the output, we introduced new procedure to minimize fluctuation. We introduced additional components to control the flow and to stabilize the flow, decoupling the distribution from the pump, more than in the past. We have two sets of control parameters, startup and run. But it's not an easy challenge to stabilize 15 cubic meters of detectors at the level of 0.1 millibar or below. Additional study that we did during LS2, the long shutdown 2, where we are at the moment, is the installation of what we call dummy chambers. These dummy chambers are volume that simulates detectors located at the highest point of each distribution sector. And they are used to have a better pressure regulation of the sector, minimizing any fluctuation during transition phases. For example, from shutdown, where maybe the nitrogen or air is used, to normal operation, where there is the standard freon-based gas mixture with its hydrostatic weight, which is important. And also, very important, to compensate for the loss of the hydrostatic column due to leaks in the detector during the short stop or power cut. This is a huge effort ongoing in ATLAS and CMS. Additional studies are position of the regulation valves. In ATLAS was done last year, and CMS is ongoing at the moment. It started 2 years ago. The idea of replacing manual valve used to equalize the pressure between different sectors, detector zones, with automatic regulation valves. This, of course, requires valve for the regulation of tens of millibar, flow of cubic meters per hour, silicon-free, because otherwise will give aging, and operation in magnetic field. They have to also to be at a price which is reasonable, because there are many of these valve needed in the detector. So we have, out of the 20 tested, we have a candidate, and we are going to see if it's the good one. The integration will be a challenge, because as you can see, the zone is pretty much crowded. So next step is the recuperation. So the possibility to recuperate a gas, this is the possibility to recuperate a gas from the exhausted gas mixture. Many systems are already equipped with gas recuperation. The advantage, of course, is a further reduction of the consumption. So we go reduction more than 90%. The disadvantage is, again, another added level of complexity. the need of dedicated R&D, because separating this mixture is something that very often is not done by the industry. So we need to develop something. And for sure, we need to develop a monitoring tool of the mixture to be sure that we are not sending the wrong mixture, we are not sending something which is causing aging in the detector, and so on. So we have, as I said, we have a gas recuperation system in many detectors at the LHC, because it's also a way to clean for nitrogen. That nitrogen we cannot remove with any catalyst, and it's also a way to recuperate in the gas when we enter in a shutdown phase. Now, the ongoing R&D is aiming in testing the feasibility of new recuperation systems. The most important one is the one for the 134A, which is going to impact ALICE, ATLAS, CMS, and ALICE. ALICE twice. And we are also aiming substantial improvement of the existing system, like the CF4 for CMS and the LCB, and the C4F10 for LCB. The 134A is important because it's the largest contributor. Of course, recuperation will be effective only if we manage to decrease the leak rate at the detector level. So the first example is the CF4 recuperation plants for the CMS CSC. Here, the problem was the presence of high concentration of nitrogen in the return flow because of diffusion leaks at the detector level. So the air is entering, oxygen can be filtered, water as well, not nitrogen. So if you want to remove nitrogen, we have to treat the mixture. The R&D started in 2009. We had a system in 2012. The system is working with 3 different stages. The first one, membrane separation, then removing of remaining CO2 on a molecular sieve, 4 angstrom, and then pressure swing on molecular sieve 13X to extract the CF4 from the rest of the mixture. So from run 1 to run 2, we managed to go up to have up to 44% reduction in the CF4 consumption, which is pretty okay. Our original goal was 50% efficiency, so we are close to that. The R&D that we are doing now will either solve the current limitation, so we go above 50%, as high as we manage, or we will see and evaluate the conversion of the last module for a cryogenic separation of the CF4. Coming back to the complexity of using a recuperated gas, so ensuring the good mixture composition and avoiding aging. Here you see, the quality of the recuperated gas was not always as good as we have today. At the beginning, we had in the recuperated gas nitrogen as well, together with 20% of argon. Now we managed to decrease the argon concentration down to 5%, so we have 95%, basically 95% CF4 with some 0.1, 0.2% of nitrogen. And the mixer has been modified to have the possibility to choose to have simultaneous injection of CF4 new and CF4 recuperated 50-50. At the level of monitoring, we installed single wire chambers at the mixer and in the gas stream to the detector to check if there is any aging in these detectors or any change in the gain of the detector that can be indication of something wrong. The 134A recuperation prototype. So this is the most important of the moment. So we had a prototype 0 that was tested at the end of 2018 in Atlas. The objective was the proof of principle of the gas separation and the measurement of the efficiency, measuring the efficiency of the separation between nitrogen and the rest of the gases, and also separation of isobutane and SF6. The starting idea was to separate the mixture using the different boiling points. So isobutane has a boiling point of -12. So we set a first trap at something like -25, a second trap for the 134A, again at -10 degrees, more or less below the boiling point of the freon, so at -35. And what is remaining variable, we expect it to be nitrogen, SF6, and so on. And this is the prototype in Atlas. Now, we know that, we realize that the 1,3,4,8 and the isobutane, they form a so-called they form an azeotrope. So an azeotrope is a mixture of liquid whose proportion cannot be alterated by a simple distillation. So our original scheme was is not working because we cannot use the different boiling point to separate the mixture. So in the first stage, nothing happened. While in the second stage, we managed to have at the end pure R134A, thanks to a repeated distillation between the cold buffer and the warm volume that we have here. So here is the typical characteristic curve of a positive of a minimum azeotrope, where you have the boiling point of the isobutane and the boiling point of the freon, and here you have the azeotrope. Only this repeated distillation is bringing to a pure R134A. But of course, we are losing a little bit of 1,3,4,8 during this process. We have tested between 100 and 400 liters per hour, and the efficiency is good. So next step is to compress the recuperated 1,3,4,8 for storage and reuse, and this is what we are doing at the moment. Then we have to study the separation of specific impurity, and later on we have to test the possibility of recuperating SF6. This has a potential 90% reduction of greenhouse gases. This is why it's so important. Here is a complete overview of the project. So 1,3,4,8 recuperation, Atlas, CMS, and ALICE, CF4 and C4F10 for the LACB, CF4 for CMS, and then a long-term work for finding possible green replacement of the current greenhouse gases used in particle detection. And this is the next topic. So it's not the first time that particle detectors have to deal with this problem. I'm coming from the RPC community, and when we were working on RPC in the year 90, we were dealing with this gas, so the R13B1, which has an ozone depleting potential. And at that time, the green alternative was the R134A, which is ODP 0, but Goldman boron potential still not negligible. And in fact, it's much less, but it's very high. The next, what they are, probably this HFO or something else. You will see more you will have more information about this study in tomorrow presentation done by Beatrice Mandelli in the Detector for Future Facility session, and the link is here. The last possibility is the disposal of the gas. Disposal means destruction. So the gas will be the fluorinated gas will be decomposed in CO2 and hydrofluoric acid. So then, these systems are, they have been developed by the industry. They are used by the industry, semiconductor industry mainly, where the gas is so polluted that they cannot recuperate anymore the gas. But the systems are expensive. What is expensive is also the water treatment plant for this ICHEP, and not easy to use. There are also possibilities for company to destroy, but the price is very high. Okay, coming to the conclusion, the program described aims in developing system allowing for optimizing the use of greenhouse gases at CERN LHC experiment. For many gases used today, at the moment there is no replacement available, no green replacement available. And also, what we have to deal with is the availability and the price of these gases in the future, because the fluorinated gas regulation may affect the price. And the price is something important. If the price is going to be 2 times, 3 times what we have today, the operation is going to be tough. We identified 4 strategies. The first one is the optimization of the current technology. So particular attention to gas system and detector operation, pushing the gas system upgrade beyond the original design, and improving or working at higher recirculation fraction. Next one was the recuperation plants. So developing new recuperation plants, for example, for the 1,3,4,8, or improving the one already existing for CF4, C4F10, and voila. Of course, I mean, these recuperation plants, I mean, the price to pay is very easily paid back by the gas cost saving. The very final alternatives is to find some new eco gases, but this is not for tomorrow. It's not for tomorrow because the detectors that we have in the experiment are there, and we can replace the detector to make the detectors, I mean, able to work with the new gases. So either we adapt the mixture to the current detector, or it's difficult to use new eco gases in the current experiment, where front-end board are fixed, high voltage cable are fixed, and so on. So greenhouse gas abatement or disposal is something which is going to solve the emission to the atmosphere. It's not going to solve the availability, the price, and so on. So all these optimization, new systems, so recursive regulation plans, as I said, they're increasing the complexity for the operation, requiring qualified personnel, and also the definition of a strict operation procedure. This is also what is required by the coordinated gas regulation. The last plots, I mean, to show the results of the work we are doing. So at the design phase, we managed to optimize 90% of the gas usage, which means 90% reduction. Now we are addressing the remaining 10%, which is zoomed here. So starting from before LS1, we started to work on the CF4 for the CSC, as I said. Then the work during the long shutdown, no data because the system were in stop. But when we restarted, we see the improvement. And we will see where we managed to go. A lot will depend on the 134A recuperation. So I finished. Thanks a lot, and sorry.
Thanks for your nice overview of the very important problem of gases at the detectors at the LHC. And now we can open this discussion for this talk. Some questions? Because there are no questions on the chat, you can.
I raised my hand
personally.
I raise my hand again if I can ask the question. This is Massimo Caccia. And you mentioned, if I don't mistaken, that the largest volume is actually the 16 cubic meter by the Ultrasar PC.
Yeah.
Just to get a feeling, to get a gauge, how much actually Europe and industrial application is using per year in terms of cubic meter? Are we peanuts or are we significant? I just don't have the slightest idea.
Yeah, I mean, I cannot say the number because they are considered confidential. But I mean, as I said at the beginning, I think in one of the first slides, the contribution from CERN is very small. Is peanuts. Is not huge. But what we have to secure is the availability of the gas.
Sure. No, this is clear.
And also the price, because I can give you an example. I mean, when we started to work for the CF4 recuperation in CMS, the price of the CF4 was 450 Swiss franc per cubic meter. Was enormous, and this is why this was the trigger to start the recuperation. I mean, then luckily, a couple of years after, the price decreased to 130. So 130 Swiss francs per cubic meter. So that we were very lucky. But in the future, we are not going to be as lucky as we were in the past. I mean, especially because the LHC is going to run up to 2035 or even maybe beyond. And I mean, already today in Europe, basically very few industry are using the 134A. And in fact, we import the 134A from China. So at some point when this gas will not be used anymore and maybe not produced anymore, the quota will be very small and the price will increase. And also, I think the development of new systems such recuperation is, I think, is a technological challenge that is also, I mean, is also a good work for the research community, for CERN, for all the research community.
Okay, thank you very much, Roberto.
Thanks a lot. Thanks.
Thank you. Still some questions? Not another questions? Okay, thanks to speaker again.
Thanks.
And no questions? No. And we can go to the last presentation of the first block. It will be given by Christine Novotny from the Johannes Gutenberg University Mainz, and it will be talk about the quantum track reconstruction algorithm for the non-high energy physics applications. So you can start.
Thank you for the very nice introduction. I would like to start with introducing myself again, because the affiliation is not up to date. I did my PhD in theoretical high energy physics at the Johannes Gutenberg University, and have been during that time a visiting scientist at the CERN theory department. During that time, I figured out that the knowledge transfer is much more important for me, and just to improve people's life positively. So I've joined GluonNet, where I combine both the scientific approach, the knowledge that I learned, I can apply there. And yes, this is what I will talk to you about during the next few minutes, how my work has the ability to improve people's life. And my outline is as follows. First of all, I would like to highlight the similarities between particle track reconstruction and track reconstruction used in aviation after a short motivation, and then focus on the particular aim of track reconstruction in the aviation sector, before I will come then to the current work that combines both sectors very nicely, which is the quantum graph neural network approach. That I will explain you this approach in more detail, as well as the current status, before I will summarize my work, the work of myself, and of course the contributors who are researchers of course of GluonNet, CERN Open Lab, Caltech, the Middle East Technical University of Ankara, DESY, and CERN. So first of all, why is it interesting to study track reconstruction of airplanes? Because first of all, there are similarities between the track reconstruction of airplanes and particle physics, because the airplanes follow dedicated flight paths, and one of the blunt differences is that in particle physics you seek for collisions, whereas in aviation industry you would like to highly avoid them, because there are always lives lost. Another similarity is the huge amount of data that is expected. In particle physics, there is a huge increase in the amount of data expected during the high luminosity run and the possible future circular collider. In the aviation sector, there is an increase of data expected as well, due to the upcoming regulations of drones, as well as the equipment, more and more frequent equipment of ADS-B senders that broadcast the satellite signal in the aircrafts. Another similarities is the object identification. So this transpond ADS-B sender has the added value that it gives, that it leads to a unique identification of an aircraft. And in particle physics, detector hits are reconstructed to particle tracks, and then you can identify the particles itself. This has led to an R&D, recent R&D study topic in the collaboration between GluoNet from the private sector side and the research side, represented by the Medical East Technical University of Ankara and CERN Open Lab, as well as researchers from Caltech and DAISY. And the aim of this study is to use, to see if the huge amount of data can be tackled by using novel techniques, such as quantum computing. So the aim of track reconstructions with airplanes is basically divided into 4 pillars. The first pillar is the improvement of flight safety, of course, and it could be used as a better prediction of emergency situations, a recommendation how to get out of the out of a possible emergency situation, as well as the incident tracking on a historical basis. The second pillar covers the anomaly detection, which is broadly spoken the detection of unusual behavior based on flight paths and the identification of the patterns. So the reason why the aircrafts deviated very strongly from their flight paths. Reasons could be, for example, that the aircraft has to avoid crisis regions or regions heavily affected by weather, but there could be any other case. Another huge pillar covers the environmental aspect. So this could be here, the track reconstruction could be used as a prediction with future data, using future data, for recommending the best possible flight path according to the data. That might lead, in addition to that, to a reduction of the carbon footprint. And this leads to, for example, the application of the sustainable development goals, as well as it might lead to an improvement of cost and efficiency, which is basically could cover the reduction of the fuel consumptions, the improvement of the airport capacity. So this could lead to more landings and takeoffs, and of course to handle better the huge amount of data that is expected during the upcoming years. So just to give you an example, a visual example, I'd like to show you a heat map of the flight data that covers 1 day. And you can see here the areas of high traffic in dark red, and you can see very nicely the shape of the continents. And if you go look into the middle, in the south of Greenland, you can see these dedicated flight paths and where the airplanes are flying because of this honeycomb structure in between. So for example, the month of April in 2019, we, in terms of the amount of data now, we can speak of roughly 500 gigabytes, and not every single aircraft has had an ADS-B sender. So if you can imagine, if you increase the number of ADS-B senders, there might be more data available to be analyzed. And one of this particular aim, as I mentioned, is the improvement of flight safety, which leads me to mention the TACAS analysis. TACAS is the abbreviation for Traffic Collision Avoidance System, and it is a collision warning system that recommends the optimal flight path in order to avoid a collision. So therefore, you could consider in quotation marks a hockey puck around each airplane, and if the two hockey pucks interfere with each other, a signal is raised, and the board computer tells one aircraft go up, and the other has to go down. In the past, there has been an unfortunate event because over the Zurich in the Zurich area there has been an airplane crash. The TACAS system worked very nicely, but however, unfortunately, the air traffic controller recommended the wrong option that has led to a crash. And since then, it has become mandatory to follow the TACAS advice in these situations. And usually, just to give you an idea how large this hockey puck is, I would like to mention that we have a diameter of 55.5 kilometers and a height of roughly 1 kilometer during the cruise. And it depends also, in addition to that, a little bit on the flight level, how broad the hockey pucks might be. And during April 2019, there have been luckily only 0.015% of the total data TCAS alerts, but of course it would be better to reduce this number because it, however, as I've said, could be that lives are lost. And in the data, for example, we've reconstructed one TCAS event. So you can see on the right-hand side. So here you can see the trajectories of the two airplanes that cross that cross each other, and that raised an alert. And if you look at this slide, so you can see every TCAS event during April that has happened in the western part of the United States of America. And when you look at it a little bit, you can see the lights of the flashlights of the events that are highlighted. And as you can see, well, in my case, I orient myself a little more on the West Coast, that there are more TCAS events close to cities. And this brings me to similarities between particle physics and airplane track reconstruction again. So there will be a dictionary for the next few slides that we will use. And in particle physics, you have a detector hit, whereas in the airplane case, this would correspond to the timestamp with the position. The event ID in particle physics would correspond to the unique ID of the airplane transponder. The particle identification number would then correspond to the airplane type, let's say an A380 or Boeing. And because I will talk in the following more about graph neural networks, I would like to mention as well that the edge, so the connection between 2 points, is we consider internally as distance between 2 airplanes, whereas the node that correspond to a detector hit corresponds to an airplane. So the quantum graph neural network is basically running for the particle physics case. In the aviation case, the situation is a little bit more challenging, and why I will come to this. The reason I will come to this later. And one benefit of the particle physics is that CERN has launched the TrackML challenge, and their data set is used as a benchmark check for the performance of the algorithms. This is why we first use these ingested data for a better comparison between the underlying circuits and different architectures of the networks. We focus here on the barrel region that you can see on the right-hand side, that is depicted in blue, red, and green, and the different areas correspond to the layers in the data preprocessing algorithm. And we usually consider 100 events. This is due to the huge amount of processing time of our networks. These 100 events correspond to 1% of the total TrackML events, and are then subdivided into 8 segments in the rapidity eta and 2 segments in the z direction. So the other applied cuts to narrow the data set a little bit more down, you can see here on the table, as well as an example graph you can see then, which is one of the 8 segments then on the right-hand side. And then we have to ensure that the quality of data is good. And therefore we plot the hit counts, so the number of hit counts versus the different variables. And yes, we see a uniform distribution. So we are happy and proceed. The quantum graph neural network itself is based on the classical approach by the HepTrax project, which is now the ExtraTrax project, as I remember correctly. And this quantum graph neural network approach as a collaboration between CERN Open Lab, the Middle Technical East University of Ankara, researchers of DAISY and Caltech, as well as the private company GluaNet. And it is aimed as an R&D study, as I mentioned, to see if it's possible to reconstruct particle tracks using quantum computing techniques. Currently, I have to say, the classical machine learning techniques are sufficient for dealing with the high amount of data in both particle physics and in the aviation sector, but the situation might change due to the run of the high luminosity LHC and the possible FCC in particle physics, and due to the increase of drones and the additional equipment of aircrafts with ADS-B senders in the aviation sector. We focus on a hybrid model of classical graph neural nets with quantum circuits. And as I mentioned before, for me, the most obvious application outside of HEP is the integration of flight data. But my colleague Steve mentioned the application to sustainable finance and sustainable investments as well, in order to recommend how to make investments and optimize the portfolio that maximize the ESG returns and minimizing the risk at the same time. Or as well, the talk, another application by my colleague and supervisor, Daniel Dobosch, who analyzed with our colleague Andrea financial transaction in order to end violence against children. And coming back to the structure of this hybrid network. I would like to explain why we refer to the word hybrid, because it's the application of a classical input neural network and then the quantum node network and the quantum edge network are applied iteratively. And the quantum edge network contains of classical edge network, and therein you reduce the input number of hidden dimensions to the number of circuit parameters. Afterwards, the number of qubits correspond then to the dimensions of the output layer, and then you can apply basically every circuit structure that you consider as useful. And then the output is ingested to the quantum node network. In the quantum node network, it's basically the same because it consists of a classical node network, and it reduces the input number of hidden dimensions to the number of circuit parameters. Then you can, then the number of qubits correspond again to the dimensions of the output layer, and then you can apply any arbitrary quantum circuit of your choice, and then its output is ingested again to the next quantum edge network. And I'd like to show you how that it looks like with a more figuratively. So you can see the node network. With the on the right hand side, we have chosen a so-called tensor tree architecture, and we have on the left hand side in dark gray the airplane of interest. We ingest its x, y, and z coordinates to the qubit, and then we start to rotate and entangle them. And we are doing the same with its neighbor airplanes. So we take the air coordinates as well, ingest them into the qubits, start to rotate and untangle them. And then we do the measurement. We have one circuit for each possible neighbor. And due to the fact that we know the exact distance of the aircrafts, we have an exact training. And this is good because for the understanding for the risk of collisions. And you have a fourth coordinate, and this corresponds to a so-called hidden layer. And what this is, I would like to tell you after I've mentioned the node network, the edge network, sorry. Here, the node features, so the output is ingested again, and the hidden features serve in form of additional qubits as an increase of the hidden dimension. And in classical terms, the hidden features correspond to hidden layers in the classical neural network, but you need less qubits for the same outcome in the classic as you would need when you use classical hidden layers. And the training proceeds. As you can see here on the left-hand side, I will explain you this in the term with the edge node network. We average of the measurement outcomes to obtain the probability that it is an edge. Then we calculate the error from the ground truth data, calculate then the gradients of the parameters. Then we update these parameters, and then we repeat the training. And so we run the circuit for n times. And as you can see here, at the beginning, the loss is high, whereas the accuracy is really low. And throughout this iterative application, the loss decreases. and the accuracy increases. We've done this for 2 architectures. In orange, this is the architecture I've shown you before. And in blue, there's a new architecture. And the difference here is that there's only one direct measurement. And you can see the plots cover one single epoch and cover the training set of 1,400 subgraphs with a validation set of 200 subgraphs. And we've chosen the Adam optimizer and a learning rate for the old architecture of 0.03 and the learning rate for the blue one with 0.005. And our observation has been so far that the network requires a smaller learning rate without having quantum circuit parameters. And now I would like to mention our current work, which is the ingestion of multiple qubits. And due to the decrease of processing time, we restricted ourselves to 4 qubits and were interested in a high expressibility, which can lead to a performance increase as well as a high entanglement. And according to the figure of the left-hand side, you would like to choose the number of the author's circuits of 6, 11, 14, and 15, which we actually did. And the color shows you the number of parameters. So just to mention, in the lower right corner of my slide, you can see the circuit number 6 drawn, and it has one of the most highest amounts of parameter, but it still performs well. We did this in addition with 2 additional structures. So one is again the tensor tree network you've seen on the slides before. We're using 5 epochs, but the learning rate is very small, which is not surprising for a graph neural network, because even classical graph neural networks need at least 66 epochs for the node classification and 96 epochs for the graph classification. Our goal is then to extend these circuits to at least 8 qubits, but preferably more. And this brings me to the next steps. We would like to vary, in addition to that, the data sets. As I said, extended to more qubits. And as you can see on the right-hand side, we have to choose our backend then very carefully, because of course we would like to have a low processing time and a high number of qubits. And as you can see from the figure on the right-hand side, we think about choosing Qiskit. In addition to that, we consider to parallelize the existing code. At the moment, it is possible to parallelize the feed of the edges because it's sequential, but the order does not matter. And we could run different quantum circuits in parallel. And we consider to use PyTorch, Dask, and Prefect for this, as well as I'm now coming back to the TECAS case. We think of apply other quantum circuits for this need, because it's the aviation case is a little bit more challenging than the particle track reconstruction. Whereas I don't get me wrong, I don't say at the moment, I don't say that this particle track reconstruction algorithm design and make performance test is easy. But in the particle physics case, the collision of particles happened and are, in quotation mark, snapshots. So this is the event is so done, so to say. In the airplanes, in the aircraft case, the airplane's position is updated every 5 seconds. And so you need to have a procedural update of the whole architecture for every position, as well as to take, for example, the nearest neighbor algorithm in addition to that into account. And this brings me to my summary. I hope I could outline that there are striking similarities between airplane track reconstructions and particle track reconstructions, that there's a variety of needs in the aviation industry that can be addressed, but it's not necessarily limited to the aviation industry. And showed you a little bit about our graph neural network that applies very well in the particle physics tracks reconstruction case, that contains of a hybrid structure of the quantum graph neural net, that there are currently tests running, as well the next steps we have in mind, which are the parallelization of the code, the variation of backends, as well as of the circuit, and the training with the flight data is ongoing. And here I would like to thank the contributors, especially Daniel Dobosch, who allowed me and stepped back so that I could give the talk. And especially the two master students I would like to thank, which are Carla Riga and Cheng Tujus, who are working heavily on the particle physics case, as well as I would like to mention, of course, Alberto Di Meglio, who's the head of CERN Open Lab, for his support, as well as to Peter Griffiths, Linda Orlady, and Jeff Ashbold for very fruitful discussions in the aviation part of this study, and beyond that they are patient and still answer our questions. Yes, for Ariane, who kindly provided us the data. I'm sorry, I will finish in a moment. And this leads me to thank you for your attention. And if you have some questions beyond the question session now, please feel free to write us an email, and as well as there is a Zoom link available.
So, thank you for your nice presentation. And now we can discuss. This is the first one.
Okay, so it's always Massimo. And the question that I have is very, very trivial. I just had a check by listening to you. The average number of airplanes in the sky in any time of the day is 10,000. And the peak number is 200,000. So my question is trivially simple. I mean, how many qubits and what is computing power that you need, presuming that you overcome other problems, to track at least 10,000 planes in the sky at the same time?
Well, just to give you a number, I don't like to mention a fixed number. Currently, we use 12 qubits, and they take up, with the current setup, it takes 2 weeks to run one single epoch. So this is just for one airplane.
Okay.
With two neighbor airplanes, so you can imagine that it.
So it's still a long way to go. And
yeah.
So,
and first of all, we need to reduce, of course, on a classical way. At the moment, the data set, of course.
May you tell me, so 12 qubits, and what is the running time that you mentioned me?
2 weeks, so roughly 1 qubit per day.
Okay. Yes. Okay. So, but any possibility to apply the same procedure but on a classical computer? Because actually the application is nice. So I know I'm going to be provocative. Of course, you have to play with quantum computers, but so far, if you want to have more fun, maybe you should try to do the same with a classical computer, no?
Yes, this is what we actually do. So for the moment, as I said, it's just an R&D study that hopefully will come true in 1 or 2 decades, because another complication would be to install quantum computers in the nose of the aircraft.
Yes. Yes.
So, well, we consider this as I mentioned, as an R&D study, and it's really fun to discover the similarities between physics and the world outside of particle physics, and we hope that it will have some real application at some point, but not within the next few years, of course.
It's going to take a while. Thank you very much.
Okay, thanks for answer. Still another questions? It seems that there are no other questions. So I want to say thanks to all presenters for the first part of our session. And I am looking forward to the second part because we are in short delay. I think that we can start at 5 minutes and 17:20 because we are almost not so. And if you want to discuss, you can discuss during this coffee break and after all session 7:30. Okay, see you at 5 minutes approximately.
Hello. We still have time for the speakers in the upcoming session to test their screen sharing. So if you would like to, just let me know. I will stop my share and then you can try it.
Okay. Okay. Tak so, we finished short coffee break, maybe without coffee. And I want to invite you to the next presentation given by Roberto Jupa from University Daily Study di Trento and ANFN. And you can see the name of his presentation here. And Roberto, you can make presentation now. Thanks.
Can you hear me?
Yes, I can hear you perfectly.
Yes. Thank you. Thanks for the presentation. I'm going to talk to you about giving you some results from the ICHEP detector on board the CSCS satellite. Before going through details of the presentation, just a short introduction on the physics case or the physics context within this mission developed and is currently operated. So as you may know, the Earth has a complex magnetic environment that's commonly referred to as Van Allen belts. It's a sort of interaction between the solar wind, that's this mixture of magnetic fields and particles that are intimately coupled to each other, and the Earth magnetic field itself. You see on the left a sort of pictorial view of what we expect when you explore the magnetic environment around the Earth. So you have to focus on two main regions. So the inner radiation belt, that's you have to, you cannot spot on this figure actually. You have to imagine to stay very close to the Earth itself. Of course, the picture is not to scale. And the outer radiation belt that's represented in this picture in green. So you have to imagine of these belts as rings where, okay, please move to the rightmost figure, where you have particles that are trapped in the magnetic field lines. So they gyrate around the field lines and they bounce up and down between the North and South Pole, basically forming a sort of shape, of magnetic shape. That's what we commonly refer to as Van Allen belt. So the main object of the mission I'm going to talk to you about is to measure fluxes and flux variations of these particles, mostly electrons and protons that are trapped and somehow guided through and along these field lines. Second introductory slide that I promise you is the last mathematics I annoy you with. This system is a sort of magnetic spectrometer. Okay, it's quite a precise system. Okay, it suffers from perturbations, you will see, from the Earth itself, of the external space itself, but there are some adiabatic invariants that you can write down just by using electromagnetics, let's say electromagnetic equations and plasma equations. In particular, you have to focus on the L number. That's a measurement of the distance, okay, of the field line from the Earth magnetic equator. So longer the distance, higher, larger the L number. And then there's this pitch angle alpha that's giving you a sort of let's say the angle between the trajectory of the particle and the field lines still at the magnetic equator. Plus, that's another number that's not important. I just mentioned there for the sake of completeness. So the inner Van Allen belt is basically made of electrons and protons. The energy is very low with the one we are used to deal with in this kind of conference, okay, 100 keV, 100 MeV. Then there's the outer Van Allen belt, mostly made of electrons, and we will see that the experiment basically mostly deal with the inner belt, apart from the polar regions where higher L, so larger L, higher magnetic lines are accessible. So any electromagnetic perturbation determines sizable effects on particle trajectories. You have to think of this Van Allen belt as an electromagnetic sponge, okay, that you can perturb somehow and influence with the solar wind, solar events, particularly dramatic events, or even entropic activity, okay, so something coming from the Earth. Let's focus on the Earth itself. What's the historical background behind the CSTS mission I'm going to talk to you about is this map of earthquakes, of high magnitude, large magnitude earthquakes just in the last century, basically. And you see that China is a country particularly suffering in this dramatic events. I report to you just two pictures from the two most dramatic earthquakes. So the highest number of tolls, of death tolls basically is given in these two earthquakes in China. So the 2008 event was so dramatic that the Chinese earthquake administration started a very important program of development to study earthquakes and seismic activity, and also to improve this kind of studies, instrumenting satellites for Earth remote observation. This is an example of what I mean with Earth remote observation. This satellite you see on the right is a French satellite that's called Demeter. You see some details about the orbit and okay, the acceptance and other stuff. What characterizes the satellites is that they are multi-payload. devices. So you see a breakout there of how many payloads they have on board. And on the left, you see what this set of payloads allows you to do when a phenomenon you want to investigate occur. For instance, here you see the electromagnetic perturbation observed by the Demeter satellite in 2005 during a particular important event. You will remember the Sumatra earthquake with magnitude 8.6. You see from the upper side to the bottom side some plasma frequency, okay? You see some perturbations. You see the density of electrons, the temperature again, and going through. You see the next to last plot is the flux of electrons, and then you'll see also protons. That's another channel, and that's the channel I want to talk to you about. So why particle? That's quite strange. If you talk with the let's say the traditional community of seismologists, particle are not a channel to study earthquakes or seismic phenomena, but actually there's something in literature. I reported here 4 examples of very old missions, Russian and also US missions, that reportedly observed, I say, particle flux enhancement and the proximity of large magnitude earthquakes. Of course, these missions were not devoted to this kind of observation. This can be well described as a sort of side effect, something unexpected, but so interesting and so potentially important that it merited some further investigations, dedicated studies. And that's the reason why missions like the Demeter, I told you, and the CSCS I'm going to describe you basically originated. So the other perturbations I told you are from space, and basically this energy you focus on space weather. You know that from the sun you have a lot of energetic particles, commonly referred to as ICHEP. They're accelerated by coronal mass ejections or solar flares. And this can trigger the solar particle events that are particularly important because they have also some technological impact on our activity. I report on the left some results from PAMELA. You see the flux of galactic cosmic ray protons. So you have to think of these protons as a background. And you see from 10 MeV to 100, from 100 MeV to 100 GeV, and you see that SEP events can actually increase their burst orders of magnitude more intense than the background. And this has important effect. It's well known. Okay, I have no time. We could discuss about what historically can be attributed as blackout, as sudden and devastating backgrounds in Canada, for instance, due to solar events, but power systems, spacecraft, radio, and navigation, also other effects are something that in literature are well consolidated. So the study of space weather, the more the use we make of the satellite networks, the more important the space weather forecasting is. And I come to CSCS, Limadu. That's the mission I talk you basically about. This is a collaboration. Okay, the satellite is the Chinese satellite I'm going to tell you about, but the HEPD, that's the detector that gives the name to this presentation, is an Italian initiative. You see here the institutions involved. Very important partners are the Italian Space Agency and the INFN, plus several universities that use lined up in a row on the bottom of this slide. You see on the left the SES picture. You see how many payloads it mounts. You have some plasma analyzer packages, Langmuir probes. You see HPM and SCM that are basically scalar coil magnetometer and the high precision magnetometers, plus what's important, you have these HEPP and HEPD that are high energy particle detector and packages. The platform is a CAS 2000 if you want the technological details. The mass is about 700 kilograms. You have a total peak power consumption that's 900 watt. And the data transmission is in the X band at 120 megabit per second. You expect it working for 5 years at least, but that's what they told you at the very beginning of the development. In reality, you'll have to resist more than 5 years because the plan now is to make up a constellation of satellites. So you have to guarantee some superimposition of the operation of the different satellites. The orbit is asynchronous and the altitude is 500 kilometers, just a bit above the International Space Station, and the inclination is 97 degrees. The revisiting time, that's the time that occurs between the satellite passing in one place on the Earth's surface and the next time is 5 days. And that's the HEPD, so the payload developed by the Italian collaboration. You see on the left CSCS itself, the yellow box. That window is the window of the HEPD. You see the breakup in the other picture and a scheme on the bottom, okay? It's quite a simple detector. You have a silicon tracker to measure the arrival direction of particles. Then you have a trigger plane that's not well visible in the scheme, plus a set of 16 scintillator planes scintillator planes read out by simple PMTs that make a sort of range calorimeters for nuclei and protons. Last, you see a LISA matrix that's used to extend the energy range 5 centimeters of LISO crystal to extend the energy range and the energy reach of the experiment. Of course, everything is surrounded by a scintillator plane for vetoing purposes. On the right, you see a simulation. What do you expect? It's low energy physics. So you don't expect surprises from Monte Carlo. And that's the reason why it's also correct to indicate this as a sort of a application, okay? There's nothing that particle physics can give you as a surprise in this kind of energy regime. So again, for the HEPD-01, another slide describing you the detector. The energy range is electron 3, 100 MeV. That's the energy where this seismic phenomenon basically occurs. Proton energy range 30 to 100 MeV. Actually, we discovered that with machine learning and deep learning, we can extend the energy reach by a factor of 3 or so. There's a crude angular resolution. That's the one needed for the pitch angle measurement and backtracing. And the energy resolution has to be good, but not so much. I mean, the competitors, as I've shown you, are not so so better. The maximum omnidirectional flux measurement is 10 to the 7 centimeter per centimeter squared per second per steradians. More or less, the trigger is on average 10 hertz. Okay, the maximum trigger we suffer in the South Atlantic anomaly, and we saturate at 400 hertz. So the payload weight is less than 50 kilograms, and the power consumption has to be less than 43 watt. Actually, HEPD-1 consumes something like 27 watt. Okay, some images from the commissioning. You see the orbits, that there are the green lines, okay, representing on the Earth hemisphere, northern and southern hemisphere. You see that around the pole, the satellite and the payloads are off because of the higher fluxes and also for attitude control of the satellite. And you have some regions that were the red one all along the major seismic areas where you have a mode, an operating mode, that the so-called burst mode, particularly sensitive, also particularly demanding in terms of data, amount of data you transmit back to the Earth. Otherwise, you have the survey mode that's a sort of averaged data acquisition mode. Now, some performance from the commissioning. You see the photomultiplier performance on the left. You see the ADC counts as a function. Okay, on the x-axis you have the PMT, and the color scale gives you the number of calibration. Basically, every orbit you calibrate your PMT. So what you want is that all colors are on the same point, okay, for stability purposes for each of your PMTs. And the stability is very well proved. So PMTs pedestals are noise stable within 1%. That's something important in space, because you don't have you have no way of intervening on your apparatus so often. The trigger rate is represented on the right. You see it ranges from 50 Hertz, 20 Hertz on the equatorial zone. Then when you move towards the pole, it increases. And you see the South Atlantic anomaly. That's a region where you are not protected by the magnetic field. So basically all cosmic rays from the outer space imping on your detector. That's another interesting figure of merit of how it works. Your detector works, gets the event rate. You see the South Atlantic anomaly with the saturation at 400 Hz, as I told you before. And you see the distribution of the event rate all along the positions, of the geographical positions on your map. So Monte Carlo simulation on the left, on the upper left, electrons and protons, they're quite well separated when you consider the energy deposit on the first plane, trigger plane, and the total amount of energy deposited in the detector, sort of better curve. And you see that in data, you have basically the same. So you are confident you're well separating protons and electrons. There are most of means 99.99% of your particles, so the particles you see. On the right, you see the acceptance. So in centimeter square per steradians, you see, of course, electrons and protons are shifted in the energy just because of the physics of interactions with the detector. What else? Science runs. Just to give you an example, on the left, you see as a function of time, the energy, as a function of the energy, we have different colors for different energy, the events per second. So HEPD is able to inspect flux variations within the minute scale. That's something unprecedented, basically. So we are just we have so many data and such a quality data that actually we are a little behind with the analysis. So we are finding interesting features, but the detector is more precise than expected. And this slide is just to give you the sense of what we are doing since February 2008. Again, the map you are used to see, because I've shown you already, as a for electrons now, and as a function of the energy, just to show you that the detector is working as expected. So the flux actually decreases when increasing the energy of the electron. For the search of correlations between the particle burst and potentially seismic phenomena, of course, you have to develop some statistical methods that are firstly to put together the catalogs from different communities that are statistical assumptions different from each other. So you develop some matrices. Here, for instance, you see the mean value of the count rates, okay, for the energy of electrons less than 10 MeV. This is the color scale. And you basically perform this background estimation for cells of L and pitch angle combinations. I mentioned you these two quantities at the beginning of this talk. And what else? Let's say space weather. Of course, you may also want to be to serve the community of the space weather with particles. I remind you that particles are quite fast and real-time probe to investigate what happens between the sun and the Earth. Please keep in mind that other, let's say, the magnetic field, for instance, it's influenced by the motion of the sun itself, whereas once a particle starts and leaves the sun, it basically goes and reach the Earth undisturbed, or let's say quite fast. On the left, you see how we distinguish galactic particles from trapped particles. First, we know the magnetic field, we measure, and so we know if the particle that we are measuring is below the cutoff, the magnetic cutoff of that position, particular position, or not. So if it is below the cutoff, it must be there, trapped, and live there. Whereas if it is above the cutoff, of course, it must be a galactic particles. As expected, we observe galactic particles around the poles. That's not the only way to determine whether a particle is galactic or not. On the right, you see that we also developed some backtracing software, giving us confirm whether the particle comes from outside the Earth system or is a trapped particle from the Van Allen belt. Some preliminary results about the galactic protons. I show you the flux. I think the most important, the point of this plot is that these points are not there without this experiment, wouldn't be there without experiment. There are models. There are experiments not devoted to this that try to infer with large systematic bars this point, but you see all these beautiful black points comes basically only from one experiment, that's the ICHEP. I just mentioned you, I mentioned Pamela, sorry, in the previous slides, giving you as the lowest energy point, 100 MeV. I show you here for protons something that's at 50 MeV, okay, so even lower. Of course, the sensitivity we have allows us also to measure, to perform the measurement on the left in different time, okay, periods, and we observe what's commonly referred to as phase weather variations, long-term variations. So we follow the sun activity with the particles. Just to finish about space weather, we collected about 2.5 billion events nowadays. We are able to well represent as a function of the L shell in Earth radii. I remind you, the L shell is a marker of how magnetically distant you are from the planet. On the y-axis, you see the energy here, and the particle counts are represented by the color scale. And you see different populations very well represented. You see the inner belt, the South Atlantic anomaly, basically. The outer belt, okay, that extends from 2 radii up to 7 radii. Of course, this observation is a lower statistics because it's limited to the pole region that we cross and we are on for a very limited amount of time. And of course, we have also some sensitivity, as you see, for the galactic particles, that's high L and high energy. I just grabbed 3 minutes to talk to you about this technology session. So I think it's important to mention the work we are doing for the CSES Limado 02 program. I told you that's the idea of the Chinese earthquake administration to put in orbit a constellation of satellites. So they asked the Italian community to construct a second high energy particle detector. So there's a collaboration that's basically almost the same of the ICHEP-1 plus several very important joinings, namely the INFN division of Turin. And the detector is quite similar to the one, also the satellite is similar in scientific requirements to the first one. Also the requests of the Italian community are pretty the same. The difference is that the satellite will be on all along the orbit, so not off at the poles anymore, okay? So what we propose as Italian community is what you see sketched here. There's a crazy time schedule to be launched in 2022, so basically to be ready yesterday. You see the structure is similar. You have first trigger plane, there's a direction detector in between a second trigger plane. Then you have this plastic calorimeter, a range calorimeter, plus a laser calorimeter that's more segmented, but basically the same as the previous detector. The main upgrade, so the major upgrade, is the tracker technology. So we propose to use monolithic active pixel sensors. So to use silicon pixel for the first time in space, but also to use a monolithic active pixel sensor for the first time. You see on the left, the picture rendering of what the new HEPD should be. You see the, let's say, the blue boxes. There are the boxes in front of the turret. Basically, the turret is the stack of 3 staves, giving us 3 points of measurements for the trajectory of the particles. And the tracker itself will be made of 5 turrets. The development is at the stage of producing turrets. So we have some prototype turrets in our hands. And the project is going to deliver the full tracker in a very short time. So this project dates back to 2017. It has been a tremendous effort because making a technology ready at level 9 for space is a very long journey. So we had to review all materials and procedures of this beautiful Alpine technology that was developed for the HELICE experiment at the LHC. We had to test and qualify for launch and operations. That's something, again, very difficult to realize. Temperature variations, minus 30, 80 degrees. Mechanical stresses that I cannot describe you. I hope you see the video. For Alpine in particular, we had to face the problem of power consumptions that in space directly translate in heat dissipation, because you cannot use coolants. You have just to use conduction, okay? As well as to reduce the rush current load. But everything went fine, looks. So the project is going to deliver. For more details, please go to the contribution I linked you on the bottom of this page. So final remarks, I hope to have been in time. So SES1 launched on February 2018. Commissioning phase ended, everything is working fine. So we are going to deliver first scientific results, both for, let's say, space-induced perturbations and Earth-induced perturbations. And also, even important, the CS02 program started, and the major upgrade for the new HEPD detector is a particle tracker that's based on a monolithic active pixel sensor. That's the Alpide, very well known. Thanks for your attention.
Thank you. Thank you for your presentation. So, Massimo.
Yes, Roberto, I have a series of small and short questions. So the first one, when you consider, say, particle fluxes variation as precursors of earthquake, and one of the key figures is actually how many hours in advance or days in advance you presume to have an indication of the variation. This is absolutely essential, and unfortunately, I couldn't figure this out from your slides.
Well, unfortunately, no one couldn't figure this. That's not a model, Massimo, or at least
satellite on hypotheses that are a bit vague.
No, there's plenty of hypotheses, and the so-called problem of the light sphere, magnetosphere coupling is something that theoretically is not understood. So this is seismology. That's not my field, but what I studied in these last 2 years basically tells me that there are different communities with different hypotheses, and the hypothesis tells you from the obvious cosmic phenomena, telling you that something is occurring compatible in time, compatible with the earthquake itself, till a few days before. But again, that's also the background, just 10 seconds more. That's difficult to clearly separate what you can consider as a precursor and what instead could be an event of aftershock of an earthquake of the same series, same seismic series, but occurring before the earthquake you're considering.
Yeah, so there is no reason for my other question. It was related to the other basic question, basic problem that you have to face whenever you want to build up a precursor system, that is to say the false positive rates. So I believe it doesn't make any sense even to ask the question.
Okay, I don't know if you want to ask the question or not. Let's say that I think the plus of this mission that basically comes from as an application from the high energy physics community is that we are introducing the culture of blind analysis. That's very important.
And so you said, if I'm not mistaken, that you launched in February 2018 and commissioning was finished on September 2018. So you nearly have 2 years of data.
Yeah.
You have any indication about how many earthquakes you had over these 2 years?
How many earthquakes? We don't measure earthquakes. We get from catalog.
Yeah.
For what concerns the particle burst, okay, we have something like more than 5 sigmas from the background, about 2 or 3 times per day, okay. But this is not corrected for the, let's say, for the known background. That's also entropic sources. Okay, there are some, for instance, there are radio emitters on the Earth, so you have to correct for, and also you have to select solar quiet period. So the analysis is still ongoing. I can give you numbers, but with very large uncertainties, so large to make them useless.
Of course, you have to train the analysis. And so knowing actually how many earthquakes you had over these 2 years above, say, magnitude 5 or magnitude 6, which I believe is the minimum, could really be a guidance to develop the method for analyzing the data.
And yes, I don't remember the number on my, but it's easy to find. There's plenty of 5. Just to tell you a number, we do not consider in the very first round of the analysis magnitude larger than 5 because the threshold is too low.
So you go higher than 5.
Yes, we set the analysis threshold at the beginning. Now we're running with 6.5.
The 6.5 in magnitude or 6.5
in magnitude? In magnitude.
6.5 in magnitude. Okay.
Yeah.
Okay, thank you.
Okay, thanks. Still another question? Roberto. So, thanks, speaker again. And we can go to the next talk. The next talk will be given by Mr. Rodriguez Peña, and it is concerning about characterization of background noise in muonography using the muon telescope. So we switch from the observation of the particles at the space to the surface of the Earth, and the stage is yours.
Can you hear me?
Yes, we can hear you perfectly.
Okay, thanks. Okay, today I'm going to talk about the characterization of background in muography using the muon telescope. This work is carrying out in the University of Santander in Colombia. So let me introduce first of all, what is muography? Muography is a technique that is similar to radiography. That is, we use as radiation source the atmospheric muons caused by the interaction of primary cosmic rays with the atoms in the atmosphere. This interaction causes a particle shower that is called extensive air shower, and most of the particles are muons. These muons can traverse along a huge amount of rock, for example, like volcanoes. And if you put a detector, a tracker detector in front of such object, you can reconstruct the particle trajectories, and you can get a density histogram or myograph that is based on the difference between the expected flux and the measured flux. So how we can estimate the density difference between the structure of the volcano? The estimation is based on the Lambert-Beer law. When a given flux phi is equal to the incident flux, that is reduced exponentially depending on the path length that the particle traverses. So the transmittance is defined as the ratio between the measured flux over the incident flux. So in the myography literature, the opacity of the structure is defined as or proportional to the minus the logarithm of the transmittance, and is given in grains per centimeter square over centimeter square. So why we are interested in myography applied to volcanoes? Because in our country, Colombia, there are around 27 volcanoes that is spread along the mountain chain, the Andean mountain chain. And our first goal is to study the Cerro Machín volcano that is located near to the municipality of Cajamarca, around the middle of our country. And this volcano is special because its structure. This volcano has a kind of cap that avoid to lead pressure to the volcano. And the volcano accumulates in the time a lot of pressure that can finish in a huge explosion that can affect several of the main streets or pathways that communicates the east part of our country with the west part. Okay, our study is based on analyze the main background sources in myography, because myography has a technique that the signal to noise ratio is very low, because we use the near horizon coming muons, and at these angles the muon flux is very low in comparison with the vertical muon flux. It's near 2 orders of magnitude lower. So the main background sources are submuons or low energy muons that are scattered on the surface of the structure and can mimic trajectories of traversing muons. Another background component is extensive air showers particles that can hit the detector and mimic muons coming from the volcano. Backward particles that reach the detector from the back, and if the detector is not able to measure the direction of the particles, can increase the noise of the measurement. And finally, events generated by multiple particles that can come from an extensive air shower or from independent events. So currently, several techniques has been applied to reject such background. One of them is introduce a absorber layers in the middle of the sensitive layers. These absorbent layers can stop low energy particles like electrons and can allow that the ions passing through the detector. Another approach is use multiple layers that help to reject events caused by multiple particles, because you can reduce the probability that multiple particles hits all the sensitive layers. And finally, to remove backward particles, there is used time-of-life system, which can determine the direction of the incident particle. And in this way, you can remove the backward particles. In our case, we use particle identification techniques to try to study the principal background sources in myography. So our detector, that is called MUTE, because muon telescope, is composed by two detectors, an otoscope that measures the trajectory of the incident particle, and a water Cherenkov detector that plays the role of a calorimeter, and it measures the deposit energy of the incident particles. And also, this water Cherenkov detector can stop or absorb low energy particles coming from the back. So we identified the direction of the particle by means of a time-of-life system implemented in the otoscope. We can reject a combinatorial noise using timing of the particles passing through the otoscope. We can classify low energy particles using the energy loss of particles in the water Cherenkov detector, and we can set a momentum threshold to remove low energy muons using the information of the energy loss, the time of life, and the tracking path length in the otoscope. So here we can see a general sketch of the mechanics of our detector. Our detector is composed by two scintillation panels that can be separated at a maximum distance of 2.5 meters and a minimum distance of 40 centimeters. And in the back of the detector, we have a cubic water Cherenkov detector, 1.2 meter side. And the electronics, the front end electronics of the otoscope and the water Cherenkov detector are installed inside metallic boxes to protect them against environmental conditions. The detector is supported on a mobile structure that can elevate the detector until 15 degrees. So let's talk about the scintillation panels. The scintillation panels are made of 60 scintillation bars, 30 vertical and 30 horizontal, for shaping a matrix of 900 pixels. These bars are coupled or having inside optical fiber Saint-Gobain BCF92, and the optical fiber is coupled with a SiPM using a mechanical device that is shown in the figure. So we first need to characterize or to calibrate the SiPM response. In the lower part of the slide, we can see the the response of the IPN, and we can see the amplitude of one photoelectron that establish what which should be the threshold for the detection. In this case, we set a threshold above 5 photoelectrons, taking into account that the main noise sources in the IPN is the darkon ray that is characterized to have an amplitude similar, an amplitude equal to 1 photoelectron, and the crosstalk a counterpulse that can reach amplitudes between 2 and 3 photoelectrons. The next step is calibrate the Water-Cherenkov detector. And the Water-Cherenkov detector has a photomultiplier of 8 inches that is installed at the top of the Water-Cherenkov tank. The energy loss or deposit energy calibration is made taking into account the energy deposited by vertical muon, and if we know that muon loss are about 2 MeV per centimeter in water, and knowing that the size of the Water-Cherenkov detector is 1.2 meters, we can estimate that a vertical muon can release about 240 MeV. And in the figure we see the char histogram, that is the char released by the particles crossing the Water-Cherenkov detector, and we observe mainly 2 harms. The first one is because the electromagnetic component of extensive air showers, that is gammas, electrons and positrons, and the second harm is because muons. So the mean of this harm is set or is labeled as the energy loss or the equivalent charge of a vertical muon. So another thing that we need to take into account is to know or to understand the cosmic ray background at the observation place. We carry out simulations using Corsica and Janford. In the first figure, we see the result of the simulation of the secondary particles that reach the ground at the observation plates. We see that the main components of this background are gammas in yellow, electrons in blue, and muons in red. So it's expected that the Water-Cherenkov detector, the main components of the charge spectra, are muons, gammas, and electrons. And then using this Corsica simulation, you input this data to a Janford simulation of our detector. Here we see the Water-Cherenkov detector that generates inside Cherenkov photons for incident electron. So in the lower part, we see the response, where we compare the recorded data, that is the solid line, with the simulated data that is composed for in the lower part of the plot, for the component of the gamma electrons and positrons, and in circles for the muons component. And we can observe a fit between the data and the simulation. So before we enter to the results of our detector in the study of myography background, we need to understand the triggering modes of the detector. we have three modes. The first is when a single panel is fired, is triggered. The second one is when we detect a coincidence between both panels, that is autoscope coincidence. And we have a total coincidence with a particle pass through the wall detector, firing the two panels and the autoscope. So the first analysis we carried out was compare the flux measured only for the WCD, that is the blue histogram, and the particles recorded in the total coincidence, that is the coincidence between the water Cherenkov detector and the autoscope. We see in the figure, in the histogram, that the flux in total coincidence is reduced about two orders of magnitude in comparison with the flux recorded by the water Cherenkov detector alone. That is because the water Cherenkov detector can record particles coming from all the directions, but when the detector is in total coincidence, we can record only particles coming from the coincident window that is limited to a given angular aperture that is minor than the wall acceptance of the WCD. Another thing that is important here is highlight that in the red histogram we can observe the electromagnetic hump, the muonic hump, and we can observe another structure that appears after the muonic hump. This hump is related with multiparticle events. Mainly this hump near to 500 MIP is because the incidence, the action of two muons passing through the detector. And this hump is not observed in the blue histogram because this component is too low that for the detection of only the WCD, it's impossible to see this component because the flux of electromagnetic and muonic components so higher than this component of multiparticle is not evident. So as mentioned before, the red one is the energy histogram of the total coincidence events. So this to highlight this component of the multiparticle events, we found that is caused by particles that coming together with a relative time between them minor than 300 nanoseconds. That kind of background we name it correlating muons or correlating noise. So to analyze how the multiparticle noise is split, we use the time of light measurements to understand how is the time relation between particles arriving the detector. We find two components, the correlated particles that I mentioned before, that is particles with times minor than, with a relative time minor than 300 nanoseconds. And there are another kind of combinatorial events that is caused by uncorrelated particles, that is particles coming from different cosmic events or different extensive air showers. And the relative time of such particles are uniformly distributed along the time. So the main component of the correlated noise is due to the correlated particles. And making a zoom of the blue bar in the left-hand histogram, we can see that the correlated particles have a mean time of life of 10 nanoseconds and can be extended to 20 nanoseconds, taking account the resolution, the time of light resolution of our detector and the spatial resolution of the scintillation panels. So until now we have classified the background immunography in the following way. We have having a 100 signal plus background data, we can split this data in 3 components. The component caused by electromagnetic particles, that is around 36%. The component of the muonic or muons, that is about 33%, and the multiple background, that is 30%. This classification is made using the water Cherenkov detector by means the energy loss. So how our signal is related with muons, we can split the muons in 2 components: backward muons or forward coming muons. The backward coming muons was estimated to be 16% of this 13%, 33%, and the forward coming muons is around 83%. This classification was made using the time of life system and the direction parameter. And currently we are analyzing the last part of the background rejection, that is the separation between submuons or muons under 1 GeV momentum that can be scattered by the volcano surface, and hard muons, that is muons above 1 GeV. For this classification, we are using the time of life information, the energy loss that determines the particle identity and the mass, and the tracking information. So with this information, you can set a momentum threshold that is established using the particle identification that is provided for the water Cherenkov detector, the time of life, and the tracking path length that the particle show in the otoscope. So with this information, we set a momentum threshold that is shown in the low part of the slide. This is an estimation of the signal we expected, taking into account the background, cosmic ray background at the observation place. We see that the electrons and muon have two separated lines, and about 1 GeV, the muons, there are the muons that we need to, or we label as signal, and before 1 GeV is the background that we need to remove. Okay, as a conclusions and future work in this field, we found that the background caused by the electromagnetic component of extensive ice shower represents near the 36% of the recorded data, while the correlated multiple particle background was near to 30%. The background, the backward muons depends on, that is an important key, depends on the elevation angle of the detector. This can vary, depends on the elevation angle. In this case, for mute, for 15 degrees, this noise was around 5.3%, taking account that the water Cherenkov detectors plays the role of absorber for low energy particles with energy lower than 2 to 240 MeV. So to conclude, as a future work, we are working in some machine learning techniques to separate automatically these background components from our signal. And it's all. Thank you.
Thanks to speaker. And now we can give some questions. Do you have some questions, Massimo?
Yes, I have my standard question. So, sorry. The very first one is a bit technical, so if you don't know the answer, don't worry. I mean, what is the dimension, what is the length actually of the bars, of scintillating bars that you use? Meaning that
Okay.
I was extremely, I don't dare to say concerned, but curious about knowing the, yes, this is it. So because I'm really curious to know how much light you get out. I guess the Saint-Gobain BCF92 are wavelength shifting fiber, right? So they have scintillating lights, they shift it to green, and then they combine to the SIPM. So if you look at the spectrum, how many photoelectrons you do have?
Yeah, this is a good question because it's necessary to understand how is the attenuation along the bar depending on the interaction point of the particle. We carry out the search test. We found that in the further point of the scintillation bar that is around 120 centimeters, the signal is about 16 photoelectrons.
16. Okay.
Yes.
So the lowest you have is actually 16 photoelectrons.
Yeah, yeah.
So you can have a fantastic separation with respect to the dot count and the crosstalk, so it's not going to be much of an issue there. No, it's easy. And then the second question is related to the TOF measurement that you had. So what is the distance between the two planes that you have?
Okay, the distance is the maximum distance and is 2.5 meters.
Okay. 2.5 meters. So I guess actually that the expected delay is going to be of the order of 2 to 3 nanoseconds. So the distribution that I see in the TOF is something I don't understand.
Okay, the final distribution, the final slide, yeah? Okay, let me, yeah,
yes,
this one, yeah. It's because I forget to mention that this distribution is normalized to 1 meter. So the particle reach the relativistic limits in near to 3.3 nanoseconds. That is the time that a particle spends.
If you now step back by one slide, so you go to number 16, please.
16, okay.
15, where you have the TOF distribution. Okay, this one, 15.
Okay.
But if I take into account your 3 nanoseconds, and I look at now the distribution, I'm a bit confused. Sorry.
Okay. A relativistic particle traverses about 1 meter in about 3.3 nanoseconds. That means that for the separation of our telescope, that is 2.5 meters, is the expected, 2.5 meters in the perpendicular way. That is the shortest path length.
Okay.
If you take into account the distance corner to corner is around 3.5 meters.
Okay.
That is a range of time of light between 8 and 12 nanoseconds.
It might be the 10 that you have in the most probable value.
Yeah, but we need to to take into account also the resolution of the pixels that
exactly.
at another
what is the resolution that you have?
Sorry?
What is the time resolution that you have? This is
the time of life system have a resolution is in, let me show you. This is in the last slide. Is 158 picoseconds.
Okay, say 150 picoseconds.
Yeah, yeah.
Under 38. Okay. Okay, very good. Thank you very much. And then again, you will be able really to detect very easily whether the particles coming from the front and from the back by the sign of the time of flight.
Exactly. Yeah.
Thank you very much.
Thank you.
Okay, thank you for your explanation. Still some other questions? No? So we can go.
Thank you.
Thank you again. And we can go to the next talk. It will be given by Kenneth Long from Imperial College, and it is a little bit different topic. It is a laser hybrid accelerator for radiobiological applications. Please, you can start.
Yes, so you can see the slide and you can hear me?
Yes, we can see you. And
okay, so so I'd like to thank the organizers for allowing me the opportunity to present what we think is an exciting program to try and deliver a laser hybrid accelerator for radiobiological applications. Our goal is that this is actually a step on the route towards high precision particle beam therapy. I hope that becomes clear as we go through. Okay, so first of all, to outline the challenges, excuse me, and the opportunities. So I guess everybody knows that cancer is a big killer across the world. In fact, according to the World Health Organization, it's the second leading cause of death globally. Radiotherapy, mostly delivered by X-rays, is indicated in half of all cancer patients. People have reviewed the statistics, and I think it's clear that there is a growing requirement for radiotherapy. I think one can distinguish two regimes. In high-income countries, I think it's clear that people anticipate a significant growth in demand. So on the timescale of 2030, I think it's almost a doubling in demand, which is expected. In low and middle income countries, on the other hand, there's an enormous unmet need. So there are many places which have very sparse access to radiotherapy. And according to the statistics, it looks as though there's about 30 million lives that could be saved by 2035 if the radiotherapy provision could be scaled up to address them. So I think it's good motivation to scale up the provision of radiotherapy, but on that scale, it really requires the development of new and novel techniques. And those systems have to be integrated in a cost-effective way in order to allow a distributed network of radiotherapy facilities so that, in particular, one can address unmet need in low and middle income countries. Okay, so the way in which radiotherapy is delivered is that energy is deposited inside the body. In X-rays, as I guess we all know, the dose, so the energy per unit volume, is deposited in a way which goes through a peak close to where the X-rays enter the body and then decays, roughly speaking, exponentially. So the long tail on the energy deposition with X-rays. If you shoot proton or heavier ions, so proton or carbon ions, then the energy deposition is following a curve like this. So for protons, there's a lower entry dose than there would be for photons. And then as the particles slow down, they go through a place where the energy deposition is very large, and that's called the Bragg peak. So how that works is described here. So you see, this is for protons, you see the relative dose having a plateau region and then increasing where the Bragg peak is. Here is the proton kinetic energy, and you can see this falls in the region where there's a plateau, a low plateau in the proton energy deposition in the tissue, this energy is falling linearly. There's ionization energy loss going on, and the ionization events are relatively sparse. As the proton is coming to rest, the energy transfers are much more efficient, and energy is deposited in the tissue at a higher rate. So you see that the energy loss per unit length is increasing, so the proton energy is going down more rapidly. The linear energy transfer, this is essentially the EDX, is rising very rapidly, and this feature of the energy loss as the proton is coming to rest is what's giving the Bragg peak. For heavier ions, you get a more pronounced Bragg peak. Okay, so the effect that that has on therapy is indicated here. So on the right-hand side, you see the treatment of a pediatric chordoma, so a radiation of the spine, which is delivered with X-rays. The X-rays are delivered perpendicular to the patient from the side and from the back. By rotating the source around the body, one is able to concentrate the dose in the spine. But because of this exponentially decreasing deposition of dose, you see that the soft tissues in front of the spine receive a significant dose. So this means you have secondary damage in regions where you don't want it. And for a pediatric X-ray, so for children, the risk of secondary malignancies have a long time to develop. And therefore, this is a feature which is very bad in that situation. By contrast, using protons, again, shooting them from the side and from the back, one is able to tailor the dose such that it's distributed along the spinal column, which is where it's wanted, and the soft tissues in front of the spine are essentially free from radiation. So you have managed to spare the tissues that you don't want to be irradiated from dose, and therefore you reduce the rate of secondary malignancies you hope later in life. So this ability to tailor the dose to the place where you want to put it comes from the Bragg peak. But in addition, you have a lower entry dose. And that means that in principle, you do less damage as the radiation is shot in. So it's great potential to develop proton and heavier ion therapy in order to treat cancer. Okay, so the vision that we have then in the LARA consortium is that by executing our program, we want to be able to create the capability to deliver particle beam therapy in completely new regimens. And the key thing here is we want to be able to make a facility which is really, really flexible. We want to combine different ion species efficiently so that they could be used in a single treatment fraction. We want to exploit ultra-high dose rates in novel spatial and spectral fractionation schemes. And I'll come to the reasons why we think those is good later. Secondly, in order to address this unmet need issue or the growing requirement for radiotherapy, we want to make best-in-class treatments available to the many. To do that, we want to reach a situation where we can reduce the footprint of the facility. And we think that one way to do that, which has promise, is to make an automated and triggerable system. And in that way, we want to reduce the requirement for a large gantry. So the large magnets that you have to rotate the beam around the patient in order to shoot from many angles. So here it's not just an accelerator problem, it's really a system problem. So we have to be able to observe both the patient and the tissues. We have to know where the dose goes so that we're able to trigger our beam delivery at the moment when the tissues are in an optimal alignment and we know that we're going to strike the target. Okay, so it's a very ambitious program. I completely recognize that. And we recognize that this is a multi-decade activity that we started. Okay, so we've chosen the radiobiology as our target for reasons I'm going to explain. So that's why the Laser Hybrid Accelerator is for radiobiological application. We think there's an opportunity here. Okay, so the one way to characterize the way that charged particle beams affect tissue is to look at the relative response of your biological system to protons in relation to a reference photon system. So RBE is the ratio of the dose required to get the same biological response with protons as you would have with a reference photon source. In the middle, you see a plot of a compilation of RBE data from in vitro and in vivo measurements, plotted as a function of dose. I think as a natural scientist, I draw your attention to the scatter of the data points and the size of the error bars. I've drawn on a dashed line around 1.1, which appears to characterize the data. But of course, we also observe that there's a large spread and that many of the data points have significant uncertainty. Of course, more is known. In particular, RBE is known to depend on the energy of the particle, the ion species, the dose, the rate at which you deliver the dose, the tissue type, and the kind of tumor or the endpoint that you are trying to address. Okay. Today, treatment planning, so the development of which dose you deliver at which angle and at which energy, is based on an RBE value for protons of 1.1. And the graph shows you how well that describes the data. For carbon ions, effective values are used, typically above 2. But again, they're characteristic of the data. They're not really describing the data in detail. So I think we recognize that if we are able to contribute to developing an improved understanding of the radiobiology, we really can make a positive impact on particle beam therapy today and obviously in the future. So there's an opportunity there to make measurements which can improve the situation. So now we work towards a specification for the facility we'd like to build. People are able to distinguish the difference between low LET and high LET radiation. So that's, I tried to indicate where low and high LET might be in the Bragg peak earlier. So low LET radiation might be photons or electrons, where the ionization events are relatively sparse. So this would also be the high energy protons that are entering the body before they've slowed down. So now the ionization events are creating the free radicals, which through chemical processes cause damage. And in this way, you can cause lesions in the DNA, and that can lead to cell death. If you have high LET particles, what you see is many ionization events closely spaced along the track. So for example, here's alpha radiation, so helium nuclei. You get very closely spaced ionization events. If you lower, as the particle is coming to rest, you can have many events that are happening across the DNA helix. Therefore, you have the opportunity to make multiple damage to the DNA, which is much harder to repair and leads to more cell death. So if you target that at the tumor by putting the Bragg peak in the right place, you can kill the tumor cells and spare the healthy tissue. And people have made measurements of the difference between the fival fraction of cells in vitro measurements, and you can see the difference between low and high LET particles. So now the way in which tissues respond to radiation is of course very complex. The easy bit really is the physical science part, where we know the electromagnetic process pretty well. We know that it happens in a tiny fraction of a second. So the physical phase here, where we create the ionization, we're able to understand very well. Then we go through a chemical phase, a biochemistry phase, and later a biological phase. And these are characterized by different timescales. So if you make the free radicals, they cause their effects in time periods that are going from, say, a microsecond to a second. And then the biochemistry is happening on timescales of hours. So it is conceivable that if you interrupt the process of what's going on to make the biological impact of charged particle impinging on the tissue, at different points in this pathway, you may be able to control the outcome or you may be able to influence the outcome of the radiation. So I think what we want to do is take a pragmatic approach. We want to create a situation where you can make dynamic studies of the impact of radiation, in particular, seek to interrupt this process at different parts of its development. And we want to make measurements such that we can interpret those, we can interpret the models and compare them with data. So we want to make sophisticated computer models by developing things such as G4DNA or Topaz, So codes which are describing the microbiophysical processes which are causing the response of tissue to ionizing radiation. Okay, so our goal then is to develop something which can do radiobiology and really make the definitive measurements. So we want to be able to access those areas which are important in the future and are not yet known. So I'm just going to present 2 case studies to motivate the need to manipulate the beams. So first of all, let's look at the temporal dependence, where recent results have shown that if you deliver the same dose very rapidly, you can have beneficial clinical effects. Okay, so let's start with the flash. That's the jargon. Conventional radiotherapy is delivered at a rate of something like 2 gray per minute, and you get multiple fractions at 2 gray per minute. In the flash regime, you deliver the dose, so let's say the same dose, but you deliver it at a rate which is many, many times faster, so more than 40 gray per second. In fact, for the photons and electrons, it's probably more than 100 gray per second. The measurements that have been made actually in 2014, so the initial reports here of order 2014 showed evidence of normal tissue sparing. So I pulled out a figure from that paper. What you see is the control sample on the left-hand side with various ways of looking at the tissue. And then you see different irradiations. So here's 17 rays of conventional gamma rays. And what the figures are flagging is where there is damage to the tissue that arises from the radiation. If instead you deliver 17 grays with flash, so in very, very fast, high rate of delivering the dose, with 4.5 MeV electrons, you see that the damage is essentially absent. And you can recreate the damage, but you have to deliver the dose up to 30 grays in flash at 4.5 MeV electrons. So you can see substantial evidence of normal tissue sparing. This was developed through experiments in mini pig and cat, and eventually the first treatment of patient was done in 2019 in Lausanne. The key thing here is that this was a skin tumor. It was treated with electrons. There was much better, so there was the same response of the tumor kill, but with normal tissue sparing. So this was a big benefit. I think there are 2 things here. There's using novel beams has allowed clinical benefit. Secondly, the route from initial observation to clinical impact is actually rather short, can be rather short. It's a motivating thing, perhaps. So that's the temporal dependence. What about the spatial dependence? Well, here again, there is evidence that different beam structures can give different benefit. So same structure of the worked example. In conventional radiotherapy, typically you deliver the dose uniformly over an area which has a diameter of, say, 1 centimeter or bigger. What people have studied is looking at irradiating the same overall area, but putting the dose in small beamlets, so in microbeams. And the goal is to put no dose between the microbeams such that you get big valleys in where you put the radiation damage. And here, what has been published is that there is significant evidence that the recovery of normal tissue is much more rapid. So it means that the normal tissue is less badly affected by a particular dose of radiation. And that means that in principle, you can escalate the dose in the tumor, and therefore you can have a greater therapeutic effect. Okay, so we want to study the spatial dependence. So our goal with LARA then is really we want to make the ideally flexible facility that can deliver all of that. We want to be able to vary the beam in the time domain. So we want to do different kind of marked space ratios. We want to deliver different dose rates. We also want to vary the space domain. So we want to focus. Perhaps we also want to collimate, but we want to vary the dose in the space domain. We want to do that with multiple ion species. And of course, we want to vary the energy. And we want to do that one at a time, but also in combination. And probably our biological colleagues will also want to combine that with chemo and immunotherapies. So we really want to make a facility which is flexible and can study that and make definitive measurements. Okay, so what's our plan then? How do we think we may be able to do that? So here's Lara. What we want to exploit is the developments that have been made in laser-driven sources, and we want to make a hybrid approach where we capture the beam at relatively low energy and then accelerate it rapidly using novel techniques. So in a little more detail, we want to take a laser-driven source which is capable of delivering a very large flux of protons or ions. We want to capture at high energy, so we want to be in excess of 10 MeV. Today, particles are captured, so protons are captured at roughly 60 keV, and by having this much higher capture energy, we're able to evade the limitation which comes from the mutual repulsion of the ions. So that's called the space charge effect, and we can therefore inject a much larger dose, instantaneous dose rate into the first accelerating element. We can deliver very, very short pulses because the laser pulse is very short. So in principle, we can make bunches as short as 10 to 40 nanoseconds, and we can trigger the laser. Our key issue then is to make sure that the post acceleration, so all the beam handling, is done with techniques which are rapid. In particular, acceleration should not use a technique in which you have to ramp magnets, which is therefore slow. We want to use novel electron plasma lenses to focus the beam. So here we can get a strong focusing system, which has short focal length, but without using high field solenoids. And that we think will reduce the cost. So we're looking really at the deployment of many of these facilities in the further future. And then we want to do the fast, flexible acceleration of our 10 to 15 MeV protons that we create to deliver 127 MeVs maximum energy to the biological samples. Okay, so here's our conceptual design. You see the laser source housed in the green objects here. The target is in this region, so that the protons are being produced at the exit window here and captured in our plasma lenses, which are shown in purple. We then want to transport and bend the beam upwards into the first in vitro end station here, where you can do experiments with protons between 10 and 15 MeV. The post accelerator here is fixed field, and therefore we do not ramp the magnets. We can accelerate rapidly. The beam is extracted. In order to do experiments with the ions, we bend up into a second in vitro end station, which is sitting here, or we transport the beam to the in vivo end station, which is at the end here. This is placed so that the animal handling can be separate from the rest of the facility. Okay, so this is the conceptual design. I just wanted to take you through the different pieces of that. So our goal is to use a technique called target normal sheath acceleration, where we shoot the laser at 45 degrees to the surface. So this is a high power laser in a very, very short pulse. So our specification is 25 femtosecond pulse of laser light. The laser, of course, has a very intense electric field. When it strikes the surface, what that does is accelerate the electrons and drive them into the foil. As the electrons go through the thin foil, they ionize the material. So they create more electrons, and they're driven through the thin foil, pop out the other side. And as they leave the surface of the foil, they generate a very strong electric field, which then is able to accelerate protons, which are deposited on the surface in a thin hydrocarbon layer. And this is sucking out the protons and accelerating them very quickly over a very short distance to reasonable energies. So this is the first observation where you see proton energies that were achieved were around 1 MeV. In modern experiments, people have developed that technique such that they're routinely delivering beams of many tens of MeV. Our goal is to back off from the end point of that spectrum so that we can stabilize the production rate and we can create a production facility. So if you look at the distribution, it comes down rapidly, and then there's a plateau region, and we want to pick off the particles in the center of the plateau region in order to be able to stabilize the rate. We then want to capture in the Gabor lens, in a plasma lens, which was invented by Gabor in all of the 50s. So that is really an electron gas. The electrons create an electric field, of course, and therefore the effect of that is that if you shoot positive particles in, they are focused. The key thing is that this is electrostatic, and therefore if we combine the electrostatic focusing here with a bend later on, we're able to select momentum and clean up the beam. So I'm going to show you that in a minute. This is a prototype of the device we want to build. in operation at Imperial College. So we're studying the results that we've got from that prototype. For LARA, we've developed a system where there are 2 Gabor lenses which are used to capture the beam. And then there's a system of a further 3 Gabor lenses which prepare the beam to be injected into this bending section where there are 2 dipole magnets and some beam transport to take the beam up to the in vitro end station. I said we want to clean up the beam. So here's the size of the beam. So this is the width of the beam for the stage 1. So the first in vitro beam transport plotted as a function of distance along the beam line. You see the way that the beam size varies in our optical system. Our specification is that we're going to deliver 15 MeV particles of maximum energy into the in vitro end station with an energy spread of 2%. So what we've done is we've invented a focus at the first of a series of collimators in order to select the kinetic energy. And then there are 2 further collimators, the first of which shapes the beam so that we cut away the tails in the distribution. And the one which is placed in the bending section where the dispersion is large is there to remove the momentum tails. And the result is that we meet our specification of 2% of the beam at the end station. That, with some quadrupole magnets we put in the beam, is able to create a quasi-uniform dose distribution at the in vitro end station. So I show you the X and the Y distribution. So over a 10 millimeter circular area, we have, roughly speaking, a uniform dose. So what we do with that is we want to shoot it through the vacuum window, of course. We want to measure the dose shot by shot in a scintillating detector. We have a small air gap to allow remote handling of the samples, automatic handling of the samples. And here is the cell layer on top of the plastic sample container in its nutrient solution. So our simulation indicates that the energy deposition of a 15 MeV proton beam, the Bragg peak is beyond the place where the cell layer is. At 12 MeV, we're putting the Bragg peak right in the cell layer. So we're able to vary the energy and therefore vary the LET, and we're able to study the different processes that I outlined before. Now we have to accelerate rapidly to the maximum energy. We've chosen to use a fixed field alternating gradient accelerator technique. It was invented in the 1950s, sort of in parallel in Japan and in America. For our application, the big advantage is that it's compact, so it has a smaller footprint, and it is flexible. It's flexible in the sense that we can accelerate multiple ion species because of the dynamic aperture in the system. We can extract at variable energy, which is what you could do with a synchrotron, but we don't have to ramp the magnets. Therefore, the acceleration can be rapid, and we can have a high repetition rate, and therefore we can seek to interrupt these processes at different points in the timescale that I tried to outline before. And we can have a large acceptance system so that we can maintain the high dose rate. This technique has been successfully demonstrated in Japan, so at KEK and at Kearns, and also in the UK with the EMMA accelerator at the Daresbury Laboratory in Cheshire. For our application, so for LARA, we've developed a system based on the design for Rackham, which is shown here. So we have 10 cells. You can see the dimension. This is 4 meters, plus or minus 4 meters along each axis. We want to accelerate using magnetic alloy loaded RF cavities, so that there has to be some frequency change in the in the RF cavities as the particles are accelerated. We have 2 for redundancy. We actually only need 1 to actually do the acceleration. We've done the optics. We've also simulated the tracking. So you can see here at the bottom, the evolution of the horizontal and vertical beta functions across a lattice cell, and also the dispersion. I picked out the horizontal phase space on the right-hand side. So this is X prime, so the slope in X, and the distance in X. And you can see that the beam is well behaved in the accelerator. It's known that for FFA accelerators, the lattice is very compressed and it's difficult to do the injection and extraction. So we've been careful to make sure that in our conceptual design, we have a way of doing that. Injection is into the inside of the ring, and to prepare the phase space of the beam that we get from the stage 1 beam transport, we have this system of magnets here, which is injecting onto the inside of the FFA And of course, we extract from the outside and eventually shoot this down the beamline, which would go to the high energy in vitro end station or the in vivo end station. Our baseline concept has a factor of 3 increase in momentum in the FFA ring. So we would take 15 MeV kinetic energy protons to 127 MeV. And for ion beams, we intended to capture at around 4 MeV per nucleon, and therefore we would accelerate that to roughly 34 MeV per nucleon. Okay, so the overall performance then, obviously there are more parameters than this, but I wanted to just pull out something which is characteristic. So what you see here is the dose in gray. So for the low energy in vitro experimental end station, I've pulled out the values for the 12 MeV and the 15 MeV protons. The dose per pulse is 7 gray or 13 gray here, with the parameters that we have assumed in the evaluation of our design. Because of the short pulse, so we deliver actually a pulse which has a length just under 10 nanoseconds is the minimum length of pulse we can deliver to this end station. And therefore the instantaneous dose rate is very, very large because of the tiny, tiny time spot. If we average over a 10 Hertz operation, then we have this kind of average dose that we can deliver to the stage 1 end station. After accelerating to high energy, you see the same thing here. So 127 MeV protons, we can deliver to both the in vitro and the in vivo end station with this kind of dose. I think actually 127 MeV protons, we're not going to shoot up through the building, but certainly this would be used for irradiation of small animal models in the in vivo end station. More importantly, for the in vitro end station is the capability at 33.4 MeV per nucleon for carbons, where we can deliver a large dose to both the in vitro and the in vivo end stations. Okay, so that brings me to my conclusions. So I think the LARA consortium has developed the conceptual design of a laser hybrid accelerator for biomedical applications. So the paper is on the archive at the link that I gave you, and we are trying now to satisfy the referees in a publication that will come out in Frontiers. The laser hybrid approach, I believe, has the ability to overcome the dose rate limitations of present particle beam sources. Because of the fact that we're going to inject at high energy, and therefore we're able to evade the space charge, the current space charge limit, which is limiting the dose at the source to first accelerator element interface. I think we can deliver a uniquely flexible facility where we can deliver a range of ion species over a range of energy, a range of total dose or dose rate, and time and spatial structures. This is very important for the experimental use and perhaps also for the clinical use. So we want to develop, in order to do the experiments, we want to have an automated triggerable system. And that can be developed then to reduce the requirement for the large grant tree in order to provide on a sort of timescale of a number of decades, a transformative approach to the particle beam therapy, which is needed to meet this unmet need. And so therefore, what we're doing now is we're trying to work with stakeholders, which would include, of course, the funding agencies, to create the opportunity for us to prove the novel laser hybrid systems in operation, to contribute to the study of biophysics of charged particle beams, and thereby to enhance treatment planning to the benefit of systems today and in the future. And I think if we are successful in delivering this program, we will, I hope, disrupt technologies for clinical application, but we will also create novel capabilities which can be spun back in to science and innovation, so into the pure science that a large part of this conference is about. Thank you very much. And before I leave you, I'm going to do acknowledgements to the people whose work I've presented, which is, of course, the LARA consortium, and I just leave you with the multidisciplinary collaboration that has formed. Thank you very much.
Thank you. Thank you for a nice presentation about important topics, and I can open the discussion. Massimo?
Yes, thank you. Very, very nice. I have 3 short questions. So the first one, I couldn't see anywhere the beam intensity that you can achieve.
Right, actually, so this is summarized here. So we assume, well, okay, so 10 to the 9 protons is what we're assuming we can deliver. 10 to the 8 ions, so round numbers.
Yeah, but
and then, yeah, sorry.
Current means what?
No, 10 to the 9 particles. So, and they would be in small bunches. So the current, I'm afraid I can't tell you what that is.
I can understand that the 10 to the 9 particles. I was mostly interested in the current.
Okay, so I did not calculate that here, but so these are the doses. So this is energy per unit volume. So I apologize. I can find out the current.
Okay, no problem. Then the second question is, it's not clear to me, where are you? I mean, which is the stage of the project? Are you constructing? Are you designing? Are you?
Oh, I wish we were. No. So we we have a conceptual design. That was what I described to you. So what we have is a simulation where we are able to show that if our assumptions, which we hope are reasonable, if we are able to deliver at source our assumptions and then the beamline that I've described, we're able to deliver the dose rates as are on this slide. So we're at the conceptual design stage. I would say that we need to do a proper conceptual design before we should build it. And very importantly, we need to make prototypes of the capture system and of the particle production system and characterize those. So we're at the beginning of the program.
Okay. Then last but not least, there was an interesting report years ago about particle therapy, where the US government concluded that actually it could be elective treatment, presuming the cost to be boiled down. Right. So now, is actually also in terms of economics, in terms of finance, the project that you're proposing comparable to the other solution for particle therapy? You're maybe too early, you know.
Yes, and that's actually what I think that I don't think it's the right moment for me really to say that it's going to be cheaper than. Okay. I think our goal is to reduce the footprint, and I've given you the target that we've got. We're taking a system approach to doing that. If we would reduce the footprint and keep the complexity reasonably low, then perhaps conceptually we can think that we might be able to get a cost advantage. I think we have a flexibility advantage on paper. Mm-hmm. And I think there's another piece here, which is that we have deliberately chosen the radiobiology endpoint. That's partly because as scientists, this is actually attractive in any case, because there are measurements to be made which will give information which does not exist today. The second thing is that it will allow us to demonstrate the technologies which maybe aren't going to work as well as we are presently hoping. The other allowed outcome from this research program is that actually protons and ions, which actually have some other problems with the way in which the dose is delivered in the tissue, maybe our detailed measurements indicate that, well, actually they're great for certain tumors, but for a large fraction, it's really the chemical kind of approach which is much better. And therefore, it is conceivable that the outcome of the program, you know, our white heat of technology feeling now will not be quite as strong. I think the really great thing, though, is that we have an opportunity to drive forward things for pure science at the same time as delivering impact to the clinical area. And if we are able to reduce the footprint such that there can be many such facilities, then we will have done a great thing.
Okay, thank you very much.
Thank you. Still some questions, or maybe one from me. What kind of laser do you want to use for this purposes?
Well, so we have specified a 10 Hertz laser, which does 1 joule in 25 nanoseconds. And that's because we believe we can buy it off the shelf. So it doesn't mean to say that that's the most advanced laser you could have. it would cost you €1.5 million, but it's risk mitigation. I think that we have a lot of in-principle work to do to demonstrate we can produce and capture the particles. And there, of course, we would want to use existing facilities and to engage with the experts, you know, like Eli or the, you know, just the people who are also working in this area.
Okay. Okay, thanks. Still some questions? Oh, thanks to speaker again. And we can go to the last presentation, last talk. We will continue with the medical topics. And the next presenter is Piero Giubilato from University at INFN Padova. And the name of his topic is proton tomography imaging for cancer treatment.
Hello, can you hear me?
Yes, I can hear you perfectly.
Okay, perfect. Thanks. First of all, thanks to the organizer and the chair of the session for the opportunity of presenting this topic that fits quite nicely, I would say, with what we just saw. So this is the other side of the problem. So assuming we have a beam, what to do with it, basically. So I'll try to summarize the advancement and what we are working on toward having a proton tomography imaging that actually helps to improve cancer treatment effectiveness. So this talk will briefly illustrate which is the concept and the reason behind using protons instead of photons for performing imaging and why it is helpful for cancer treatment. So we already saw in the previous talk, so I'll go fast on that part because actually we had already an excellent introduction. So the very same old story that if we have to target something, especially well within the body, let's say a tumor on the head, what could be the prostate or whatever else, and we want to target it with usual X-ray, so photons therapy, we clearly have to deal with the problem of the energy release since the photon enters the target. While if we exploit the well-known BET block energy deposition for ions, we can exploit the Bragg peak, so where the particle releases most of its energy, to pinpoint the tumor cell we want to kill. And this peak has a width of the order of the millimeter, so the precision in principle is extremely high. That further allows us to tune the position, so to perform actual targeting by changing the energy of the beam we are injecting into the body. So this is a well-known principle since the 60s. Only in the last, I would say, 20 years, we will see the number that did start to get widespread because the availability of practical accelerating machine that could fit the budget and actually the real estate of practical therapy facilities. So here, as you already saw for the spinal cord in previous talk, this is, for example, for other part of the body, but on the left you can see the collateral dose you are giving with standard X-ray treatment, even if you can improve by increasing the number of entrance points. But even with just 2 entrance points only, you can see on the right, with proton therapy, the improvement in sparing healthy tissue that you don't want to affect. And the same we can have even for more difficult target, even within the brain. So the advantages are clear, I'm not gonna show in numbers, but for some tumors, like the one on the eye, the effectiveness of proton, or even better, ion therapy is even over the 90% mark for some specific tumor. So potentiality is there. And here, just as a view, that is with no mean as the goal to be complete, here we see where things did become practical. So from the 50s to the end of previous century, when we start having machines compact enough to accelerate protons, at least, or even heavy ions to the energy required. Just as a recall, we are speaking of energies between around 200 mega electron volt for protons. Superconducting magnets further improved. So as you can see, this picture starting the century, we went below 100 tons for the accelerating machine. And with the latest design, with traditional machine, we just talk with much more advanced ideas. Anyway, we are now able to get to almost manageable size and weights. That means that in principle, as you can see in this picture, and this is actually practically done, in some cases you can avoid the transport of the beam, and you can rotate the accelerator itself around the patient. That clearly makes it much easier, the dealing with the focusing of the beam and in general with the transport of the beam, which is minimal, but also simplify the facility. So this is just one example. There are many other approaches to the problem, but that to show how the hydrotherapy is really gaining ground because of the technological advancement that are making it practical for real use. So that shows that, in fact, almost all advanced countries are building and expanding their capabilities in that respect. So centers from the Americas to the East through passing through Europe. And if we look actually at the number of facility, we can see that from the end of the 90s, in fact, we have a marked growth where the green line here is how many facilities we have in the world that reached and surpassed the 100 hadron therapy facility marks a few years ago. And you see that in the latest year, we have on average 8 to 10 new facilities being built or opening each passing year. So definitely the interest is growing, and from practical technological application, of course, even the market interested for whatever concerning hydrotherapy. So this is super short summary of what is the therapy status. What is one of the problem, apart the big one of having a small enough machine to make it practical? So here we are. We saw that basically the idea is to aim with a proton or ion beam. I'm using proton to stay simple, the tumor within the body. And tuning the energy allow us to pinpoint with millimetric precision how deep we go with our beam. And actually, present machines can give us a precision on this energy well below 1%. That actually translates when we get better than 1% in, let's say, 100 or 200, which is 100 the energy to stop the proton within a head, or even lower energy. When you get down to 1% or better, you are also approaching the theoretical limit in precision that the particle straggling is giving to you. So with energy tuning of 4.5%, the precision is there, and it's a physical limit. The point is that to be precise, you don't not only need a precise energy tuning, but also you need to know the density of the tissue your particle has to move through, because the density will change the energy release of the proton, the particle, therefore changing its range. So you need two things to have perfect aiming: high energy precision and high precision in mapping the density of your target, of the human body in this case. And here is where the limit at present is. Why? Because at the moment, to take a 3D image of the target of the body, we use, of course, X-ray computed tomography, which is the golden standard. But X-rays, while have extremely high spatial resolution, have much less density, so stopping power equivalent resolution on material. And that limits our precision on the resolution mapping of the target to about 5%. So you can see we have 0.5% in energy, but only 5% in tissue density. And this represents the present limit of ultimate precision in aiming our ions to the tumor. So on the right, I used an example that I frequently use. So it's an X-ray image of a very common plastic pen. As you can see, you have excellent spatial resolution, but we are not seeing the ink nor the tube containing the ink. Now you can see an example of the same pen, image taken with protons. So you can immediately see that the spatial resolution is definitely lower, but you can distinguish plastic, the ink, even the tube containing the ink, the plastic cap, and so on. So protons, by the very way they interact with matters, are a more precise probe when it comes to stopping power of matters. And here is the same image with some different reconstruction to show you that you can anywhere retrieve, if not as good as X-ray, but a good even spatial resolution. So this is the point. The idea is to use proton even to take images and not only to perform the therapy. Even more interesting, to take this sort of images of a human body, you need almost the same energy range the accelerating machine is able to deliver to perform the therapy, because with, let's say, 200 MeV proton, you pass through a human body, releasing just a small amount of energy. So you can get basically imaging with the very same beamline you use for therapy. So what's the idea? Let's say that we have a 200 MeV proton that pass through your body. And here it comes the main difference respect to the standard X-ray tomography. Because of course, proton scatters, so you cannot just take an image of the exiting proton to see which have been absorbed or not, like for the photon, but 200 MeV proton will not be absorbed mostly by the target, the body. So you really need to track them exactly in any tracking experiment. So you need to get their entrance point, the exit point and angle, and measure the residual energy. Those data, so energy loss, exit point and angle, and entry point, will allow you through most likely path or other algorithms or transform to actually compute by injecting the proton from different angles, as in X-ray tomography, that will allow you to reconstruct a complete 3D image of the target with the required precision in density. So, which is the difficulty of doing that? That you need a sensible, I would say, number of track, around 1 billion track, to reach the resolution you need on a 3D target the size of a human head, just to give you a reference. This number is within a factor 10, could be 10 to the 8 or 10 to the 10, depending on various factors. But with 1 billion, you exceed the resolution, the theoretical resolution you can achieve, basically. And you have to do it fast because the target cannot move. So if you see immobilization device for hadron therapy, they are quite scary. And the problem of breathing remains, even there are extremely good attempts to account for it in imaging. But the idea is that if you can keep the exposure time below 10 seconds, that is a practical time to allow at least the movement over 180 degrees of the gantry, you could, if you're able to track 1 billion proton in, let's say, 10 seconds, you could take images with the necessary resolution, in principle, even avoiding the breathing of the patient. So this is clearly the final goal of such a system, but is not that far away. So last part of the talk is how to build such a scanner to get this 3D image. And this is a project that has been funded by European Research Council and is managed by Padova University and Padova INFM with the help of many other groups, of course. First thing to consider quickly, I'll not spend time on that, but just to show you that you have to think about a practical solution. So something that will work on a real medical facility. And the real medical facility for hadrotherapy mostly used what is called a paint beam. So here is a nice image from Heidelberg, if I remember right. So you can tune the energy, but you also scan the beam that is mostly focused with a spot size of 5 to 10 millimeter. And you scan through the target by modifying the X and Y coordinates, and the energy you can, as you can see on the right, completely paint your target. If you want a device that physician will like to use, you need a system that you can mount of such kind of beam. So I spare you the detail. These are practical nozzle facility you can find. And as you can see, they pattern the target with spot, and they are extremely fast. So they take 1 millisecond to jump from one position to another. And they can deliver a current that if you do the math, here is, for example, a real example of a scanning beam, you come up with these two numbers. So you have your scanning beam. We can imagine to make the scanning area homogeneous, because when we run the beam for imaging mode, so to speak, before the therapy, clearly we don't need to target a specific area, but we want a broad image. But nevertheless, if you want to cover an area of 10 by 10 centimeters, so to speak, let's say in 10 seconds, with the characteristic of the beam, you will end up with a beam that has a flux, a rate of about 100 megahertz square centimeter before entering the patient body. As you get significant scattering within the body, at the output of the body, the number of on the right highlighted, you'll have a rate per square centimeter of around 10 megahertz square centimeter. So between 10 megahertz and 100 megahertz is the ballpark your system should be able to cope with if you really want a practical system that can perform imaging in a realistic clinical environment. There is also the option, some facility have even the focusing capability that is much easier scenario where you get the focus beam with some 12 by 12 Gaussian distribution, but not even Gaussian, almost flat as you can see, and a per centimeter rate of around 1 megahertz. That is much easier scenario, but unfortunately, this is not what you find in most of the facility. So if you want a system that is able, and you want even to market it at some point, it has to go as fast at least 10 megahertz per square centimeter. So which is the main link with, I think, with the topics of this conference. So if you want to realize something like that, what you want is a very large, fast, and thin sensor. Why? Because, so this is an ideal sensor. You want something that is as big as 8 by 8 centimeter, that can, in principle, handle up to 100 megahertz per centimeter, at least 10 megahertz, that has extremely low power consumption because you cannot cool it. Why you cannot cool it? Because you cannot afford any support structure. Why? Because we are using 200 MeV proton. They scatter like hell. So if you don't want to completely spoil your measurement, you need a tracker that is as thin as possible. That means that the silicon cannot have any support. So on that principle, what you want to build is some large detector that is read only at the periphery, because you cannot afford nothing in between. And you want to put few of them together until you cover a relevant area to make the imaging of your target realistic. So this is sort of ideal detector that is not yet here. So I think many groups are working towards such side and speed detector. Even include one I part with INFN, but still not there. So what we did, we are actively working on such a goal in our project, but to start with, we did use the excellent ALPID sensor from the ALICE collaboration that at present, you know very well, is likely, definitely I would say, the most advanced and large area monolithic sensor available to the scientific community with speed characteristic that can approach what we need for this application. So we decided to use for the tracker this very sensor. You can see on the right a photograph of a pen, as usual, that has been taken with 70 MeV protons at the TIFPA beam line at the Hydrotherapy Center in Trento, Italy. So our tracker is composed by 3 layers of ALPID sensor, and we were mounting it, but unfortunately, due to a COVID crisis in February, we did stop with only the first 3 of 15 staves installed on the final tracker. So here, unfortunately, I cannot show you any 3D image because our tracker, we will start building it likely, unfortunately, only in September when with the lab and the workshop will open back. But as you can see, the idea we used actually to give credit the staves developed by ALICE because they were the most lightweight ones, so less material budget. And compared to the ALICE experiment, we did take away completely all the cooling system because the cooling is air cooling. As we can afford it, we can assess the detector from top and bottom. So we got rid of the cooling pipes and the cooling facility to further slim down the detector and minimize the material budget. Then to conclude, we saw that this is a scanner. So the tracker requires a very large sensor and low power one. Remains the problem of measuring the residual energy of the proton. And here we did exploit the same solution as the therapy. So the Bragg peak again. So to make it short, our calorimeter is a range calorimeter where we have alternating plates of scintillator that is further divided in small scintillator of 5 by 10 millimeter and 20 centimeter length, alternated, as you can see from the picture, in the X and Y plane in an orthogonal shape. What is the concept? We have a silicon photomultiplier reading those scintillator, and the scintillator with the highest signal is the one that, so to speak, captures the Bragg peak. Even better, by interpolating the signal of the 2 neighbor scintillator respect to the one that got the Bragg peak, we can improve the resolution actually down to better than 1% of the range. That translates mostly in an energy resolution of 1% that is, with this technique, at the limit that again is due by the struggling of the particle in the calorimeter. So here you can see the actual calorimeter being assembled. So you can see this very thin 5mm scintillator. We explore many material and silicon photomultiplier, and the array of silicon multiplayer that is composing one module. We will have something like 12 modules like that, orthogonally interconnected, forming the calorimeter. On the bottom picture, you can see one, an orthogonal, so two modules like that are put one side each other, and two other are put orthogonally, so completely closing the volume with the scintillators. Does it work? That fortunately we almost completed before the COVID. So here top left, you can see the signal from the silicon photomultiplier, the analog one, for a proton crossing them, stopping in the orange one, the one with the highest signal, and having some residual energy in the other scintillator. Each scintillator is 5mm thick to give you the scale. So you can clearly reconstruct the Bragg peak, but we have to go fast. And for doing that, reducing the data, the silicon photomultiplier output is fed into a custom-made 4-bit, sorry, error on the slide, 2-bit ADC running at 500 MHz. As a 2-bit ADC was not in the market, we had to make it from standalone components. That is not ideal, you see the picture. But this allowed us to make up a 3-threshold system. You can see the picture that directly feed an FPGA with a digital signal. This is enough, as you can see from this plot, to distinguish very well the scintillator with the Bragg peak, the scintillator neighborhood of the Bragg peak, and the scintillator where the proton is just passing through. So the calorimeter works, and this is one of the final module with 2 FPGA on top of it that we were assembling in Padua before the COVID. So this is now we look forward to complete it and put it into operation. The plan was to show you the images and the result by this conference, but the COVID did altered it. One note, this is the custom-made electronics that read out the array of silicon photomultiplier and digitize the signal and then feed it into the FPGA. It is clearly not efficient. It was made because we had no time to develop a custom-made ASIC, but clearly by simply adapting some extremely good ASIC that have been designed within INFN for PET scanner, basically lowering the number of digitization bit, this entire bulky part of the electronic could almost be reduced to a single ASIC. So this is clearly a prototype, but we are already looking forward on how to make it a more practical design. Once we demonstrate that the entire version is working, we'll definitely look for moving to ASIC design. Last thing I want to show you, and is again about, as this is a session on technological, is practicability of solution. So basically you saw we have a calorimeter that is working. We hope to complete as soon as possible the tracker. And for our scanner to work, we need to have something around 112 high-speed link, where an high-speed link is more than 1 gigabit per second. If we want to keep the imaging time within 10 seconds, that is the goal. So this is a very reasonable number for any modern high-energy physics application. So that would not be any problem. Point is again that you want a system that is commercially practical and you can put in an hospital. So you don't want a crate of high-speed board. Plus, such a system, as anyway you have the halo of the beam, should transmit while the beam is on, giving you concern about the radiation tolerance of your system. But we clearly did want to stay away from systems like the GBTX that is fantastic for cover news at CERN, but again, is not something you can want to deal with in a system that has to be commercialized maybe one day. So how we did work around that, I think this is something we are reasonably happy with. So we did choose a commercial FPGA module off the shelf with 1 to 2 gigabyte of memory for each FPGA DDR memory. So how does it work? At the end, we have a distributed system that between the calorimeter and the tracker has some hundreds small FPGA distributed. The FPGA nowadays, the basic one, are reasonably cheap. So you can get down to some $100 per FPGA. So the cost of the FPGA system is not gonna killing you. And so all the data from the acquisition, both from the calorimeter and the tracker, are locally stored. Protecting from radiation corruption stored data is quite easy because over a billion tracks, even if few are corrupted, you simply don't care, so you don't protect it. And while there is the radiation on, you do not transmit. And literature and experience on protecting and operating FPGA in a low radiation environment is enough to guarantee operation, so the work is already done. After the data are acquired in 10 seconds, you read them out. How do we read them? With completely stupid and commercial USB connection. Why? Because at the end, even the basic USB 3.0 gives you 5 gigabit of bandwidth. That is more, comparable with what we have with GBT. And if you upgrade to USB 3.1, 3.2, or Thunderbolt 2, you can move on up to, with the present state of the art you can buy in the market, with 40 gigabit per second. That means that even the full tracker and calorimeter can be downloaded, so to speak, in a few seconds by using completely commercial apps and technology. Furthermore, you don't have to deal with your own protocol or whatever, and you have an extreme flexible topology. For example, for testing, as I try to highlight in the picture, we connect with a single USB our module directly to the computer. We perform all the calibration testing, and without any change of anything, we can build up a system that is composed by tens or hundreds modules. So the idea of using a completely commercial technology that is makes possible by the fact that we can, the radiation is not continuous, of course, so we have time to download the data. Anyway, saved us a huge amount of R&D time and did provide us with a very practical system and solution. So after that one, I come to my outlook and conclusion. And so that talk was about medical design of a system that is mostly a sensor, a thin one we saw, and a calorimeter, in that case, silicon photomultiplier and scintillator. The key point for us was to keep, as you can see, low voltage, no gas, lightweight, ultra fast, because we want something like in this rendering that we can really apply to a clinical environment. So we cannot exceed much more than some 50 volts in our depletion voltage or something like that. We cannot cryo-cool the things nor anything like that. And that is possible if we go for large sensor with low power consumption, so monolithic sensor that, as you can see, are direct derivation from what found in high energy physics development. Which is the nice part? Of course, there are many things in common with next generation high energy physics tracker and calorimeter from what we saw. And we are plenty of solutions that have been originally developed for high energy physics. My feeling is that actually is already happening, but nevertheless in the near future, there will be common ground for those sort of large sensor, definitely in the biological sciences that are lagging behind on that respect, but could hugely benefit from the application of this sort of sensor to other kind of imaging. I show here you some example of super resolution microscopy for biology or electron microscopy for material science, where large sensor, where with large, we are speaking of, let's say, 4 by 4 centimeter or something this order of magnitude, will be extremely beneficial. And we are speaking of sensor with built-in data sparsification, so no imager from the camera. And least but not last, because again, it's connected with what we just saw in this session, clearly, as Roberto did show, space application, because again, here, large area and low power are the two key elements, not forgetting that a monolithic sensor is monolithic, so is intrinsically extremely reliable in a super demanding environment like the space one. And that basically is the conclusion of my overview. So I hope to convey at least what is my view, that in the next future, or even basically in the present, strong cooperation could lead to huge advancement, which can benefit an extremely broad field of scientific and applied research. And that's all from my side. Thanks for your attention.
Thanks for your presentation. And now we have the possibility to give some questions to you. Are some questions? No questions here?
I have a question, actually.
Okay.
So, Piero, thanks a lot for your nice presentation. So you're using the scintillator calorimeter. Do you think that, do you envisage other calorimeters which would be equally good candidates? Or do you think that the scintillating one is the one to choose for this application also in the long term?
So excellent question. The other obvious candidate is a tracking calorimeter that you can realize with the same sensor you use for the tracker. I think this is the most obvious candidate when it comes to same precision and speed. So the precision in energy, that is your ultimate benchmark, is at some point limited by the physical process itself. And on that respect, both kind of calorimeter reach that benchmark, so they are fine. Tracking calorimeter gives you a further handle in 3D reconstruction, because you can distinguish with high precision even the position in the calorimeter of the proton. That we do only partially, and this is the reason I had no time, because you can see in this picture that we have segmentation. But our position resolution in the XY axis is of, let's say, 5 millimeter, while a tracking calorimeter could be much better. So why we did choose this one? First, is cheaper to start with and gives us full coverage of the 3D volume. So I think that when reasonably cheap sensor of many centimeter will be available, that I'm quite convinced will be in the next 5 years, I would say that a tracking calorimeter could be even easier, because at the end you use the very same system that you are using for the tracker. You know, so you simplify your whole design. At the moment, that was the most practical solution, to have a real calorimeter working and a reasonably cheap one in the amount of time of the lifespan of the project. That is how we see it.
Okay, thank you.
Okay, thanks for this answer. Still some questions? No. Thanks to speaker again. Thanks to all speakers of this session. Thanks also to all participants. And what to say to the end of this session, we could see that many results of research of high energy physics can be successfully applied and the various fields of human activities in medicine or the cancer treatment, for monitoring of the volcano, earthquake, quake, monitoring of the particle activities around the Earth. New algorithms were developed for increasing safety of the air traffics. New strategy was developed for the gases in gaseous detectors at this LHC. So it is fine. New neutron detectors were developed also for the neutron detection. So it is fine. And I think that the research at high energy physics has a sense not only for the high energy physics community, but for all people. So it is fine. And if you want now discuss, you can discuss still approximately 1 hour together. And if you want leave, you can leave. And I wish you a nice rest of our conference. Unfortunately, it is virtual, but better virtual than none. And I hope to see you in person at the next ICHEP conference, and maybe at the ICHEP conference in Prague, which can be in 2024. Thanks to all, and see you.
Thank you.
Better times.
Thank you. Bye.
Thank you. Bye-bye.
Thank you very much, Miroslav.
Walter, thanks.
No, it's fine. So I think thank you for doing all this work, and yeah, I think you organized the session quite well. So thanks a lot for all the work, and for yeah, I mean, I think it was a nice session actually. So
yes, it was nice. It was relatively small but nice. So it was not so much work as for neutrino physics.
Okay. All right. Thanks again. And then I'll talk to you later. Bye-bye.
See you. Bye.